Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. I hope you caught my intro there. Okay, I think we're online. We shall see. Thanks for joining me this evening for Magic Incarnate. This is the presentation that we will be discussing today, and I'll put my head down in this side of the frame because when I'm looking at the screen it makes more sense. Anyway, so we're going to be talking about the Hutchison fracture sample tonight, and today for you in the US, and thank you for joining us. There's been some interesting news today and over the last few days. One of them is that apparently some studies have been finding mushrooms on Mars, so I now have a new foraging destination. Certainly I would say that the determinations of puffballs being on Mars are reasonably fit with my understanding of what puffballs look like, being absolutely obsessed with mushrooms. And so that's very interesting, and lots of other different types of lichen type structures and saprophytic type structures and their fruiting bodies. So it's not a surprise that if you go anywhere on Earth you find life, even in the most inhospitable places, and I would expect that to be the case anywhere that life is even remotely possible in the universe. There will be life. The other one was that a contributor to the Thunderbolts project has seen the light, that actually ball lightning might be accounting for some of the UFOs, and that's interesting. That's the kind of conclusion I came to a few years back now with the Hessdalen lights, and I called the blog there on the Steemit channel UFOs over Hessdalen or something like that. And I did a study of that, and you know, I think what I think you will see in some of the commentary I'll make tonight with respect to the fracture sample is that actually the technology that makes ball lightning is the technology that you will use for anti-gravity. It is the technology that you will use for probably faster than light travel. It is the technology that you will use for incredible mining technologies, construction technologies, to end scarcity, unlimited energy, teleportation, all the things that I've kind of been hinting at over the last few years. But I have to say that this is not an original thought. This is something that Ken Shoulders spelt out quite clearly in his papers over the years, and it's only by seeing these things occurring in experiments that you can understand where he was coming from, and hopefully we will share some tonight that I think you will find interesting, and others. Now, the thing is, whenever you look at a sample, and the sample we're going to be studying today, I have actually shared a lot of data on over the last couple of years. If I can find it. Oh no, that's it. No, I thought I'd lost it. Is this fracture sample, and we're going to show you some beautiful macro photography that I've taken of this with stack focusing, so you can get some really good look at what it looks like, and they will be in the book when that is produced, but you will see me scrolling around on it today, and so you will get an idea. And we're going to talk about, in the first part of this presentation, the things that probably are just basic normal things that occur in metallurgy. Now, I'm not the world's greatest expert in metallurgy. I did do material science in my university course. I'm no expert. So at some points today, I might be saying, this looks like it's interesting. I would like you to go away and see if you can find you know, the same thing occurring in some other science. So there's 2 points, one where it looks a bit like it's super fluidity, and another one where we are getting something that will be right at the end of the presentation, which is just absolutely completely mind-bending. It's completely mind-bending, and not that you guys need any encouragement, but I want to do something for this, because I want to help you try and prove that this is nothing out of the ordinary. Okay, and what I will do is, I think one or two times in this presentation, if I get to it, I will say that for those people that find significant proof that some of the things that I'm sharing with you can be explained by a completely ordinary thing, and that thing is fully described. I will send you a book, this book, Space, Earth, Human by Alexander Parkhomov, and so I would be very happy for people to try and find an alternative reason for a couple of things that I will talk to here today. Okay, so magic incarnate. Okay, now what I'm going to try and do a little bit better today is to not give you just my mugshot when I'm trying to tell you something. The first part of the presentation will be more organized. When we get to the end, it's more raw data we'll talk through because I want you to go away and think about it and come back with suggestions of what's going on. So what you're looking back at in the background here, now I'm going to actually go and get a big mouse pointer because we'll be doing a lot of mouse pointing waving today at the slides, and so it will be useful to have that so that we don't cause people to struggle to see where we are meant to be looking. Okay. And can everyone hear me? Can everyone hear me? Okay, got a nice fat cursor. There we go. Lovely. Okay. Okay, so what you are looking at here on this background here is the area we'll come to at the end of the presentation on the Hutchison fracture sample. And it has several features which appear in large areas of this particular sample. And they tell a story, and perhaps you will be able to work out exactly what that story is in time. Perhaps you won't. But I believe it's certainly very interesting. And the things that I want you to think about is what's hiding under this eye over here, what's over here, and what's over here, and what's over here, and this sphere that we have here dotting the eye. Those are the things we're going to be looking at. And what you've got down here is magnesium, silicon, and iron. And there's a phase relationship between them, and a kind of like outer phase relationship. So it's not the case that every time you see magnesium you see silicon, and it's not the case that every time you see iron you see silicon as well. So it's a little bit weird, and that is why this is tied with the sort of cold nuclear transmutation and ball lightning. And we shall go forward. So, not necessarily in this order, we will be discussing the sample, what's normal, potentially, what might still be normal, what the normal stuff may cause the apparently abnormal stuff, why the normal stuff, get my teeth in today, why the normal stuff may cause the apparently abnormal stuff, and what may be abnormal. Okay. Perhaps I should have said diverse or something, I don't know. So, just so that you see the slide there, that's the whole slide. Okay. So, this is the fracture sample as it was received at the end of 2017. And we shared this macro image, and it's sample 4. And what we're going to discuss are these points here, the splintered wood appearance that rearranges and then binds into place. So it looks like these are almost pieces of wood, and they have splintered away from a large piece of wood, and some of them have reorganize themselves such that they are facing in different directions, and then for whatever reason they've bound themselves back to the large mass of material. Now the reality is that most of these pieces here I have given to third parties to analyse. And none of them have analysed it, or none of them have analysed it and sent the data. However, I did try. So this is the sample as it was received, and I've already showed you another example, and I'll go and get it again. This sample here, which is the same kind of thing. So I wasn't feeling too bad about sending away or giving segments of that of the original splinter sample to other people to look at, because there's this much larger sample here, you can see relatively, that has many more of these fragments that have moved around and then fused onto each other. And so that is that. We're going to look at the flat fracture plane morphology, and that is the structures that you see in the areas which have split. And then we're going to look at various exotic vacuum object, Evo Quanta, which we have looked at before, but I'm just going to revise that. But you can go and look at the previous presentation that I've done on that. And then the red crystal-like inclusions in the center of vortex features, and how that might be relevant to what happened in the synthesis of this material. And then element composition and spatial arrangement. And that is where it's going to get very, very interesting. We've already done some of that with this sample, but like I say, the cover slide, there's a lot more to show. Okay, so now here are the stack photo macro shots. And what you're looking at here is the front side, the back side, and here you are looking at the top, as I call it, and the bottom. And as you can see from the previous shot here, all of these pieces do not exist now on the sample because they were given away in good faith, and so they don't exist on the top anyway. So it's much simpler as a piece of metal now. Okay, so what I'm going to do is I'm going to zoom into these features, and I need to go and find that image set. And the first one we're going to look at is this, and this is the bottom. And if we go right into it, and we'll go into this even more, there are dendritic grains going on, and you can actually see it's an accretion here on the back side. And you can see here again, it's an accretion. So this whole area here is like a dome that's attached to an otherwise different piece. And the thing about when you are forming or casting metals, you get these dendritic growth depending on the rate of cooling and temperature gradients and stuff like that. Now, I have to say, John wasn't going to a pure metal supplier and buying very expensive 5/9 grade pure homogeneous known crystal structure metals. He was going to the scrapyard and picking up bits of metal, or buying metal in that way, or acquiring metal in that way. And that may have been to his advantage, as I will argue in this presentation. Now, it makes an analysis job a little bit more difficult because you don't know what it started with. But you can infer that if this was an industrial metal, that maybe it had a certain alloy composition, and that whilst this is said to be aluminium or aluminum, it may actually be an alloy, and it would be unreasonable to think that John knew it was pure aluminium at the time he got it. And the fact that it may not have been pure aluminium may be very, very important to different observations between different samples that John had. Okay, so I'm going to go and have a look at this much closer, and then we're going to just talk about dendritic structures. Okay, so give me a second, I will go and find those images. Okay, I think I'm probably ready to show this. Okay, so we'll just have a look over the samples themselves, the blow up, and it's quite rather nice, the resolution I have here. So you can see the dendritic structures here. So there's one here, and you can see the typical dendrite structures. Now normally this would be growing into a void with a vapor, or it would be growing into a metal or metal solution, and there would be a nucleation point, and it would grow from that point. Now over here we see these very linear structures. Now what is this? Could this have been resting against a rat tail file at the time when it was somehow changing? I don't know. And we can see here, you can see the dendrites on the end here. Now this is something that's well known in metallurgy, so don't get too excited. But when I get to it, you will see that when dendrites grow, they can change the elemental, if it is an alloy, which I expect this was, they can change the elemental composition in between the dendrites themselves, leaving a different material property in between the crystals that eventually compose the metal sample. Okay, so let's see what the other next slide is. This is the close-up. Now, when I looked at this, this kind of rippled texture, I would have ordinarily completely thought that this was some sort of sand casting artifact. And I did hold that belief for a long time, and it may actually be true. I mean, it is reasonable to say that if you're picking up scrap metal, that at some point it may have been sand cast. And this piece may have been sand cast. But as we go into this, you'll see that maybe there's other explanations. Okay, so you can see just like Africa and South America fit together quite nicely, but not quite. You've got that kind of thing going on here. And the interesting thing is that also the split planes have the same kind of structure. And this is something that we will look at. Okay. This is the front, as I call it, and you can see that There's a large piece that comes up here. I have to say, when you take a photo like this, it it makes it look quite beautiful. The previous shot, I had two different color lights. The original photos that I took of the samples had two different colored lights. So one was a warmer light, so you had a contrast across it. That gave you kind of a left side, right side illumination. This is very white light that is on the macro lens, and so it gives a kind of much more kind of like consistent lighting across the sample. If you ever get a chance to get a Hutchison sample, he ships them as paperweights, and I think they're quite beautiful as a paperweight, you might like to say. So this is the backside, and actually you can see this piece that sticks up a huge way here. I actually wasn't able to get that in the stack shot here, and so that is why that bit there is out of focus, because it's coming towards the camera way more than I expected. Okay, so I'll need to do another stack shot for the book, but there's a little gloopy little bit on the end here, which is quite cute. So this is a rather brain-free, taxing-free look around the sample. And you can see these are major fractures here, and you can see how tightly that this fracture aligns with this, but it's kind of slightly also out of place. I mean, did something disappear in this bit, or was this moved around? This definitely moved, but it's kind of locked in here. Okay, so that's a look at the sample, and we can start addressing some of the things. So the first thing I want to talk about is dendritic grains. And I don't know whether I shared this, but maybe I did, maybe I didn't. I'm going to show you this presentation, and it's from Ames Lab. Well, it's got several people involved. I think it's from the Institute of Museum and Library Services, and the link is on the slide from the dendritic grains that I've already given you. And there's a couple of things in here which I find quite interesting. So it's talking about, you know, when you've got a material, you've heated it up, and then if you cool it very slowly so that the system is always at equilibrium, then freezing will occur isothermally. And it talks about, you know, when something freezes, you get heat liberated upon freezing. And this is what I'm saying about electron condensates. When they are going into this new phase of matter, they will have to release heat. And there's a couple of ways they can do that, but one of them is maybe to eject 2 kiloelectron volt electrons or photons, UV light, these kind of things. And that is a way of getting rid of energy so that the electrons can condense. And this is in every phase change when you're going from something that has more energy in it to something that holds less energy. It has to liberate some form of energy in order to go to that lower energy phase. Okay, so it's quite a long presentation. I think one thing that will be important to think about here is the nature of these crystals that you're seeing here in these ice crystals, which I think we can think back on. And then here's your dendrites, and it's a whole discussion about what's special about the solid-liquid interface. And here is some large dendrites formed, and this is in a shrink head of an ingot of gun steel from 1899. So you can see a sketch of where they came from, and they sort of grew into this void here. This is an interesting point, those that didn't know it, and it speaks back to that 1950s paper that I was talking about, where you have the speed of vibration of atoms, and it's got 10,000 gigahertz, so 10 terahertz, so it's terahertz. That's atoms vibrate at 10 terahertz. Is a nice thing there. And if we go down, you can get an idea of how this is working, but I didn't make this presentation, so I'm not going to present it. This is showing nucleation points growing together, and then you end up with your crystal grains here. And this is what Ken Shoulders said: exotic vacuum objects don't like to travel across. And it's also what Matsumoto observed, the formation of what he calls microball lightning or itonic clusters in crystal grains, and then they eat the crystal grain boundaries, and then end up eating the crystal, and he finds material disappeared inside his reactor. So it's showing here some dendrites growing, and here's some pictures of dendrites. And if you compare that to our dendrites here, it's not precisely the same because it's a different metal, but same kind of thing. Now, we saw these dendrites growing and effectively instantaneously in the tungsten that was exposed to a Mars gas and then touched the PTFE in Project Omar. Except it must have come out of a plasma state, and this is what Solin calls instant formation of crystals with cavities from the coherent matter. Now, I kind of like this one here because it looks a little bit like our layer here on the back of the fracture sample. And I like the commentary here. It says, the surface of an ingot of antimony showing dendritic crystals which have grown to interference with each other. That is what we have here. These have grown to interference with each other. Okay. This pattern was the mystic star of antimony of the alchemists, about half its natural size, photo courtesy of the Science Museum, London. I thought that was quite cute. So it talks about the phase boundary and how the crystals grow in, and so on. Anyway, so the dendrites by themselves are not something that is not known, okay? And they've been well studied. So they grow up like this, and then lower down they end up having these kind of like puffy cells. Now, why I'm showing you this next slide is that you can have elements that are part of an alloy coming out of the alloy and forming a semi-regular array. And when we look at some previous data that was shared, we can ask whether that could account for some of what we see in the observations on the material. And then you've got these interfacial properties. So this is how you can get some semi-regular arrangement of material on a sample. And it's talking about casting and so on, and different. This is copper, tin, so forth. So anyway, that was something to think about with respect to the growth of dendrites. Now, the next part I'm going to show you is the Evo Quanta, and we've talked about this before, and I'll lose my mugshot there. And on the top left here, you can see a little bit of what you were seeing on the outside of the macro shots, but there's finer detail on here, and this is what Ken Shoulders would say. When you look at John Hutchison samples, you see evidence of exotic vacuum objects. And I've talked about this before in its own presentation, but we've got one here, 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 and I've measured this one. And so these are strike marks. They are a D4D ratio, and they have a little bit in the middle. The little bit in the middle can be bigger or smaller depending on the level of the impact of the exotic vacuum object on the aluminium. And so when measuring this one's radius to the center point, it gave a radius of 20.3 microns, so that's 40.6 or 41 microns diameter. Okay, this one up here is got a more hexagonal shape to it, but this is the limits of the Dino Light microscope for me for resolving things with any level of certainty. And so I wouldn't want to try and find quanta that are below that. In fact, there's another one there that's hexagonal. There's a pair, one here and one here. Okay. Now, stepping up to the next kind of level, and like I say, it doesn't matter what level they are, you always get a little bit of mushiness on the boundary. So this isn't the perfect diameter of it, but you can see that they are effectively regularly that size. Then the next level, you can actually see some outies and innies. And I've shared this before, where you can see these are clearly hexagon structures on here. This is what I call an innie, and this is an outie. And so I've measured two, and they're in the range of sort of diameter is 90 to 100, roughly, microns there. Okay. Then we step up to the next level. Now, I talked about this in a recent presentation where I showed this view of this particular strike mark. And I said there was another view which showed that the central point that I'm talking about here, the central point that I'm talking about here, and the central point that I'm talking about here, this central point at a different angle. And you can see here is the central point at a different angle. And you can see the radius here of the swept material. The swept material. So what you were looking at here is a bowl. It's like where a donut has hit the surface. There is actually a hexagon shape around this. It's obscured a bit by the red. And there's swept material. And you can see it's swept up like this. It's swept round in an arc. Okay. And this you'll see as things get bigger, these get more obvious their nature. And you can see also that this piece over here on this side is swept up as well, and it kind of obscures. It's in the foreground of this bit here. So what you are seeing there is a different angle on this structure, and the substructure is the 50 micron. So it's this classification. So this is 50 micron diameter, 100 micron across. This is the 100 micron across subquanta, and this probably, if this was D4D and it's 100, this should have a subquanta of 25 microns. So this one's a little bit bigger than this one. This one's a little bit bigger. This one's a little bit bigger. This one I recorded as 20.3. So this is actually what is it? That's 50 microns. So that's not right. That one wouldn't fit with that one. But anyway, this one is 100. That goes into here. That's 100, and this is 400 across. So this is D4D, and if we go to the next quanta, you take the big one here, which is 400 across, and the arc goes into the material. So you can see it sweeping the material out. And in fact, you almost have this like these sloshing, as Ken Shoulders called it. You've got a slosh there, and you've got a slosh there. You've got a slosh there, and a slosh there. And they're like little petals. And I imagine it that the subquanta swept material out, and it's turned it into this extremely fluidized aluminium, and it's just washed over the surface. Let's go back. Washed over the surface. The same thing is happening at this quanta, and you can see it swept it up, and it's just swept it up, and swept it up in the center, or it's going around like that. So whatever quanta it is, it's able to manipulate it with extreme ease. And so you see these petals, this sloshed area. And Ken Shoulders has got very, very similar imagery. And obviously, as this is now 400 microns across, If this is D4D, then there's an 800 micron central section in the center here. And that's going to be, you know, it's not even going to, you can see it affects a small area here, but leaves the center quite free. And on the inside here, on the inside here, it's had to pinch it. And as it gets out, it gets bigger. And so that's that. And in this one, I'm looking, you can see the sloshing area over here, the sloshing area here, sloshing area. This is the edge that I've picked out, but actually, because it only goes partially into the surface, you don't see the full diameter of the lower quanta. So whilst I've measured the radius here at 750, I imagine it's more like 800 microns, and the overall large structure is 1.6 millimeters across. Okay, and it came in at an angle and sort of crashed down, and so you have a slightly distorted shape. Now these things are all over the surface, but in some areas they appear to have made a very regular structure here. And this is what I was talking about, these crystals here. Now, I don't know if you can see them, I hope you can, but you can go and get this image in a number of places in different videos that I've done. And when I looked at these little crystals here, you have the innies, which are the holes, and then you have the outies. And the outies, I think it's with the outies where you have the crystals. And I thought, well, maybe this, when I first saw this, are these leftovers from being using, say, red sand casting of the aluminium? And then I played with this for a very long time. But then I got thinking, when I looked at the jewel outside here, and I've got the jewel in a different place in the presentation, so it's a little further down. I'll show you. This slide's out of order. It should have been here. This is the jewel, and this is from the Lion reactor. And the jewel is exposed to the same reactor, the Lion reactor, which looks like this, and it's quartz, okay, and it's a tube furnace. And then the actual core of the reactor is inserted into the tube furnace. Okay? And if you go back to that previous shot here, you can see here, this is the heating solenoid. And so the heating was coming from the solenoid. And it's being reflected and insulated by the foamed alumina here, aluminium oxide here. And so this quartz, which has all gone green, was exposed to essentially exactly the same temperature as what's going on here. And so I hypothesized that something must be protecting this, or at least reducing its exposure to the emissions from the reactor and the heat and overall circumstances that the rest of the reactor faced. Thank you, Brad. And so the other thing is, it only on the inside, it has this thin layer, which we will look at in a little while. But this is quite glassy, the fracture plane, but it would appear that this is like a Star Trek shield, that it was impenetrable other than it had to absorb and deal with the radiation coming from the reactor, be that thermal or whatever. And this is rose quartz. And the interesting thing about rose quartz is that you can make rose quartz from normal quartz by exposing it to beta particles or X-rays. And exotic vacuum objects produce both. Okay? Exotic vacuum objects produce both. So if you were to assume that EVOs were coming from the core of the reactor, which we're pretty certain they are in the Lion reactor, and they were forming a structure in this place for whatever reason, they would be still emitting X-rays and beta particles. They would affect the quartz, and then what you do with quartz is you heat it up to about as hot as your oven will possibly go, a little bit higher. So maybe 300 degrees centigrade. And that will cause the quartz to go, if it's not overly exposed, if you do too much to it, you end up with this. So this is EVOs going into the material, but this is, in my view, EVOs that were protecting this piece of quartz from EVO flux. And so this behaved very differently. But if we looked at the edge of this, we see that it has these vortexes all over it in a regular array. And some of them are innies, like this one over here, and this one here, and some of them are outies, like this one. Okay? But more interestingly, they go across the edge. And here is the edge of the quartz. This is the edge of the quartz. And I think it's actually, I can't remember, I think it's this bit here. Okay? And so this is a glassy, homogeneous fused quartz cylinder. And it's only affected the outside. Okay? This, on the Hutchison fracture sample, I believe is a largely homogeneous aluminium alloy macro grain. And these are taken with the Dynalite, sorry, not the Dynalite, the Narugo microscope on a Samsung S7. And they're basically at the same magnification. So the quanta on here that you're seeing, if these are exotic vacuum objects as a mesh, almost like a graphite layer. It's like a graphite layer. And you can imagine all the EVOs, they're likes, they repel each other and they attract each other. Okay? And they form this mesh. And it's formed this mesh over here. But of course, this is just quartz. That's all it had access to. Over here, something else is going on, and we can talk about that another time. But there are other elements in here. So it might be the case that these red spots here are other elements that were in the alloy, but then the vortexes around this piece of aluminium caused concentration of the material into the core of the vortex. And we've seen this with the flux loops in other areas of Lion and in other experiments. So I'll go back to this slide. So are these nucleation points? And by that, what do I mean by nucleation points? Well, I think it was 2016. I found this paper about, and I've talked about it, about the work that was done with microwaves in the 1950s, where they found, I think it was the University of Manchester, maybe I'm wrong there, but I mentioned it recently, where they found that if they use microwaves in quartz, they could get the quartz to use its piezoelectric property to convert the microwave into a soliton that contained the microwave vibrational frequency, and that would propagate at the speed of sound in quartz, reflect off the backside and come back. And I suggested that when I visited the Hutchison lab in, I think it was January the 6th, 2018 in Germany, that what might be happening is on the surface of the aluminium you had a material that was piezoelectric, and it was able to convert the RF into vibrations at the RF frequency. And when you extend that, you get to the point of understanding that if you're forcing a vibration at the frequency that the atoms are kind of attuned to, that you might be able to get to a situation where they are in phase and therefore they become coherent at whatever temperature they are. So it may be the case that what I originally thought may be sand grains from a casting process, or a silicon oxide based, or an other piezo ceramic, like little bits of quartz, could end up being the point at which coherence begins. And you get a little bit of coherent matter around the little structure there. And it could be the case that, you know, when people show you experiments done by cooling down cesium-133 atoms or sodium-23 atoms or whatever, they're cooling it down to get the atoms. In those cases, they're both silicon. Cesium is one isotope, 133. Sodium is one isotope, it's 23. So you're cooling those down. They are the same atom. You get them at the same temperature, like near absolute zero. And so they end up with the same de Broglie wavelength. And then they only need to just about get into phase. And then you have a blob of coherent matter. What I'm suggesting is that these little quartz crystals, which may have been from casting, and they're in position, they are interacting with the RF that is being fed to them, and they are producing vibration at the frequency of the RF, physical vibration, which could potentially get the vibrational mode of the aluminium around them into coherence. And then you could imagine that the whole scenario, the whole thing becomes cohered, and effectively wherever that crystal grain was, maybe that becomes effectively one superatom or one coherent matter enveloping the whole thing. And whatever's inside is, as it would seem from the Vega experiments, it loses its mass and inertia, and it's basically controlled by this skin that is coating it. So I've talked a bit about the cooling and the crystal dynamic. I've talked about the Ohmasa gas and the PTFE with regard to the instantaneous formation of crystals. The line jewel is only on the surface. Now, perhaps we can look at this sample here. I mean, I can show you actually just very quickly. This is the coral twist sample, and the interesting thing is here it hasn't fractured, and I'm going to talk about why I think that is. But what I noticed when we cut this in Sochi in Russia to do the EDS analysis is that it's only a very small thickness of the material that is affected on the outside of this structure. So there's no kind of crystal fracturing going on in here. And I think that might be because of the type of aluminium. I think different types of aluminium that John Hutchison had would have behaved in a different way because of the impurities. Let me go and find another piece. So I think these two were the same kind of aluminium. I'll go and see if I can find another piece. I can't get it immediately, but anyway, my point being is that some aluminium may be cast in a certain way. It may have different cooling regimes, it may have different alloys, and some might be drawn. And I would imagine that these kind of samples are drawn aluminium so that they end up with long crystal structures, and that goes some way to explaining why we see this kind of like woody kind of texture going on. So I want to share something that I did a transcript of Ken Shoulder's interview in 2010 with John Hutchison, and you can go and see this on the Steemit channel, but I will go to the next slide here, and I just want to draw out a couple of quotes here from Ken Shoulders from that. He says, "You name something that you want, that you need to be good, and it'd probably be the thing that does it for you. Say, anti-gravity. The propulsion properties are just incredible. It will be able to push anything you want I'm not showing you the slide, am I? Okay. Say anti-gravity. The propulsion properties are just incredible. It will be able to push anything you want, anywhere you want. It enshrouds stuff. This is all written in some of these things on the web. When it enshrouds things, it can allow them to disappear. It does make atoms disappear in my laboratory work. Well, that's interesting, you know, because when they disappear, I can transport all this stuff through to somewhere else and it reappears. That's teleportation. So it does that very nicely. As an energy source, it's just incredible. We can forget all of our energy problems. We can forget all of our propulsion problems. Okay? So, in a little while, we'll get to the point. People are probably asking me, why aren't you doing Something Electric Part 2? My real problem with Something Electric Part 2 is I have to get it right. And two, it's almost impossible, and it's not that I want to, but it's going to be a much larger presentation as a result, but it's almost impossible to walk through how you make a direct electricity generator without immediately saying exactly how to do propulsion using this technology. We already know, in my view, how you can enshroud stuff, and whilst it's enshrouded, it will lose its mass and inertia, and possibly, depending on the state of the EVOs that are enshrouding it, it could lose its charge as well, which means it can literally teleport through things. So when I'm showing you these images here of the fracture sample, and at the same scale, the same innie and outie skin on that sample, which I have said is protected. Now, when I say protected, it's not unaffected. I mean, there's still X-rays, and there are still beta particles going through this quartz, and it's still receiving the heat from the back side. But from the front side, the quartz is affected. Now, I want to show you how that is affected, because as I've just shown you with this sample, the damage is skin deep. Now, I won't go into what's actually happened to the material inside in this presentation, but we already know it sounds not a lot like straight aluminium. But anyway, the surface is only affected a small amount in depth-wise. And I'm going to show you on the jewel here. So this is a jewel. And if we're looking down at this corner point here, there's a radial set of beams coming out from this bottom. And you can see it here, radial set of beams coming out. Okay? And you have these spots. Now, these spots might be just considered nucleation points. But remember, this was just a piece of amorphous fused quartz that it started out with. And what I've done is I've taken the microscope to this top edge. And the top edge actually isn't affected in quite the same way as the edge on the side here, where the EVOs have wrapped themselves round. Okay? The skin didn't wrap itself round here. It kind of came here and just came to a dead stop. Okay, so maybe it was growing from this point and radially growing out, and maybe there was something over here and it was growing between these two, or growing from this point. Anyway, the point is there's a curvature arc here, and it got to a point and it kind of stopped. And if I show you that, on the top surface you have these scallops. You can see scallop, 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 scallop. And there's a certain depth here, and this depth here is on the long depth, it's 100 microns, and it's on the short depth, it's a 17 micron depth. And I would imagine that this is a 100 quanta EVO that's 50% into the material, sorry, 200 that we showed earlier on the, where is it, up here. So we have a 200 quanta evo. This one here, this 200 quanta evo that I've shown from two angles. Okay, we have a 200 quanta evo here and a 200 quanta evo here, and we know that they tend to intersect. They tend to intersect. Okay, we can actually see it over here. There's a two. This is one of our heart shapes here. It's actually here on the big version. So you can see that this is a blown up area here. We've blown it up. And we've got a heart shape here, and I've blown it up over here. And I'm not showing you, am I? How embarrassing. Oh dear. This is the money shot. So what I'm saying is, something came from here. Okay, I like the red hand. That works. When did you not see it? Oh dear. Okay, so we've got this... We've got this jewel here, and something radially came out from over here. Okay? Radially came out. And this area here, around this edge, is where we see the evos going on the inside and the intersection side. And this is the edge, this edge down here. Now, on the top edge, this effect doesn't go round that side. It's kind of like it got to here, and that's the skin. This is the Star Trek shield that nothing can penetrate, except the evos themselves spit out X-rays and beta particles, and hence with the heat you end up with this jewel being rose. And this is actually a standard technique for colouring quartz gems. So you start with a piece of quartz like this, and you expose it to X-rays or beta particles, heat it up to about 350 degrees, and depending on the amount of beta particles, depending on the amount of radiation and the amount of heat, you end up with different things going on. And one of them is actually this, you actually get this green stuff going on here. But anyway, so I'm looking at this, and I was referring to this being the jewel which has come out of that now. And the radial area I'm talking about is down here, this radial area. And these are the so-called nucleation points. And what I was showing is that I was looking at the top surface here, okay? This is the top edge, and you see you've got a scallop, you've got a scallop, you've got a scallop, you've got a scallop, you've got a scallop here. I've zoomed in, I think, to this area up here. A scallop, and this length here is around about 100 microns, and this is about 70 microns, okay? And I'm saying that we observe ball lightning or balls of fire in our Vega experiments 50% into the structure. So you've got it around here. You've got this ball here. So the EVO might be actually on the surface here, but its field is around there. And this is 200 microns, okay? And that is this quanta of EVO, this one that I've got from two angles here. Is that right? Oh, maybe I've done something wrong there. It's a quanta. This is 200 microns, so this is a different quanta. So I don't know. That's not very clear. So whatever it is, I'm saying that there is an EVO that's 200 across here, and you're seeing the scallops as they self-organize. And within that area, they get affected to a degree, but outside of that area, there's essentially no change to the structure. So this is what they call smoky quartz, and this is rose quartz. And there's a hard cutoff. There's a hard cutoff, and that's the shield. I believe that this was an EVO shield. And like as I was saying, when you couldn't see, they intersect each other. They intersect each other. And we go over here. We have one of our heart shapes here with them intersecting. So we've got one here with a spot in the center, one here with a spot in the center, creates this heart shape. There's the spot and the spot. So it's intersecting, and this one is intersecting. This one's the one that's on top. This one's behind in this case. Here's one on its own, a much bigger one up here, much bigger one. And I've scaled that one. This one is 122 diameter. And this one here is one side of it. It's slightly smaller this side. Is 70 diameter. Okay. And we've seen these kind of structures on the PTFE affected by a Mars gas. And interestingly, you see, but on that, you see something going between one side and the other in the same way that you kind of see it as you do here. You see it going from one side to the other. Note, this is on top of this one. And if we go back to what I just showed you, where is it? This one is on top of this one. So, you know, it's the same thing wherever you see it. So what I'm saying is that this is only skin deep, and what I am saying on here is this is likely only skin deep. And what I think is going on is what is being talked about here, where it enshrouds stuff. This is all written about in some of the things on the web. When it enshrouds things, it can allow them to disappear. Well, in this term, it's kind of allowing it to disappear from being affected by the radiation in the same way that the rest of the material around here was affected by radiation. Okay. Now, can anyone think about what this might be similar to? Because when this patent came out last year, it was kind of like, oh, you've got to be kidding me. Anyway, I'm going to show you another section from another writing of Ken Shoulders and draw it some correlation to what we are seeing here. So this is the piezoelectricity induced room temperature superconductor. So this is exactly what I was saying at the beginning, second week in January 2018, based on the 1950s patent. But I was referring to any piezo material on the aluminium. What I believe we may have, as I've been discussing, is that these are quartz, little quartz crystals, which may actually be sand that happened to be in there from some casting. But anyway, it's not a bug, it's a feature. Okay, so how do we enshroud ourselves in this magic carpet without getting burned? Okay, so this is getting burned, right? We are getting burned. This is not getting burned. This overall structure is not getting burned as much as this is. Okay, but ideally you would want something that takes all of the flak. It gets the really burned bit where the EVOs are living, and then you have other material behind. And you know what you might want to do really to make this work is have something that is metallic and conductive, and then something that's diamagnetic, and then something that's metallic and conductive, and then something that's diamagnetic. And if you wanted it to fly, you'd probably use a structural material like aluminium or magnesium. Probably magnesium. You'd use magnesium. Maybe something refractory, if you could mix that in there, like zirconium. But anyway, and then you would want something that's diamagnetic. And the most diamagnetic material you could possibly have is bismuth. And so if you were using this technology for anti-gravity, those are the elements you would naturally choose to use. And you would then layer it, because you don't want to have a scenario where this is going on. You want to be well behind several layers. And as Shishkin says, if you want to protect yourself from exotic vacuum objects, and Shoulders says, you need many thin layers. Okay? Well, these are probably the thin layers that you would want to have for these reasons. Okay? So he says, the subject now turns to trapping and the use of the trap as our magic carpet. Perhaps using one of the all-metal circulation traps resembling a giant superconductor as described in earlier EV patents by Shoulders. Resembling a giant superconductor as described in earlier EV patents by Shoulders. And then the next sentence is, EVOs don't obey fluid flow laws either. Okay? EVOs don't obey fluid flow laws either. So it's superconducting and superfluid. Superconducting and superfluid. What have we been saying we are seeing in the Vega experiments? It looks like it's superconducting and superfluid. In fact, if you look at other writings by Ken Shoulders, he says that it's quite a stiff structure that it can form, this condensed matter. Okay? So I would argue that probably with the patents and papers and the observations of John Hutchison and Ken Shoulders, you can make a room temperature superconductor, and that is the principle behind which you will be able to, with the right layered material, have a structural material that you could use with EVOs to negate gravity, and then you could use other properties of EVOs to provide propulsion. And you can use other properties of EVOs to provide unlimited energy. You getting me? Okay, so the next slide I wanted to talk about is I want to move on to superfluidity. Is there any questions there? Sorry about the losing the slides. Okay, so magnesium is basically the lightest structural metal. You can have an alloy. It typically is an alloy. Can combust in air if it's thin enough. So you tend to alloy it. Often it's alloyed with aluminium, but you can alloy it with other metals. And bismuth obviously is very heavy, so you wouldn't want that very thick maybe, but you would certainly want it to provide the diamagnetic repulsion for the EVOs, and then probably to protect yourself against the weak X-rays. The 2 kV X-rays won't get stopped, won't get through much. Well, the X-rays I think can be higher energy, but anyway, you'd need just basic shielding because they're not very high energy. I think the highest energy when an EVO explodes is typically, I think, something like 130 kV or something. So you would need some sort of, I don't know, basic lead or something. But it doesn't matter about the weight because it really doesn't matter about the weight. As Tesla said in 1910 in the Sun, New York, is it 1910 or 1911, 12, something like that, between 1910 and 1912. The thing can be of any shape and any size and be of any weight, basically. Okay, I'm going to go on because I've got a lot to get through. And it's already nearly 11. Okay. So the next slide I want to share is this one. And why am I sharing this? I'm sharing this because I have actually already shared this. It was one of the first pieces of data I shared from the fracture sample. But this speaks to what Ken Shoulders was talking about here with EVOs don't obey fluid laws either. This is an area on the sample, the fracture sample, and the bulk of it is aluminium. You can see it here. The bulk of it is aluminium. It's this orange color. So everywhere you can see orange, it's got a rich amount of aluminium. Okay, but there is a shadow, and there's a shadow that gets darker to the edge of here, which matches the line here. Okay, and so, you know, there's something slightly thicker here. And this actually looks almost like an ice crystal end. And then there's a line that runs down the center. And it's like it's growing. It's like it's growing from this center line. And something is flowing out. But it's very odd because even on this image, I thought like this is a valley when I first saw it. I thought, oh, we've got a valley here. So whatever it is, it's flowing down here. Maybe it could be some sort of iron salt. And the salt is, you know, flowing across the surface. And then it's drying out and it's leaving this crystal here. And here we can see the iron. So it's a very, very strong signal. There's basically no iron around. and there's iron here, and it gets strong to where you get to the edges here. So it kind of like gets to the edge. But as you look at this, it doesn't matter whether you're in the valley on this ridge here or on the top. It seems about the same thickness, and it looks like the same density on the element. In fact, over here, you've got a bit which is right at the tip. The tip is the brightest part, the very brightest part. And, you know, why is that? Why is this tip here, for instance, is on a ridge? It's on a ridge, but it's the brightest part. And it's bright all the way down that edge. It's bright all the way down that edge. So it doesn't matter whether it's on a ridge or a valley or a ridge. It's still the brightest part is the edge. And this kind of said superfluid to me because it's able to flow wherever it likes, to be honest. The other thing is there's no carbon here. There is some carbon in this structure, which may be detritus on the surface. And there's no oxygen. There's no oxygen. Now, I would imagine the aluminium would have some oxygen in it. But it doesn't seem to have a lot of oxygen. But the iron doesn't have a lot of oxygen. It's like it's pure iron. But is it because of the thickness? Maybe it's because of the thickness. But it's very striking, this growth on the surface. So my intuition that this was Evo's carrying this material and then depositing in its superfluid was kind of peaked when I saw this, because this is without a doubt a steep rise and fall in this direction, and it's a steep rise and fall here. You've got ridges on ridges. Okay, so you've got ridges here that are kind of basically orthogonal to the macro ridge that's coming down here. And you actually have a crystal that's coming up here, and then the crystal's going over and under and 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 finishes up over here. It's bonkers. It's growing that way. And it doesn't care that the ridges, it doesn't care that the ridges are there. And in this case, you could argue that the ridges formed after this one grew out here. But that is kind of, the problem with that is that the iron is growing up the apex of the ridge all the way up here. Look, this is the element iron, the green area here. It's growing up the apex of the ridge, growing up the apex of the ridge, growing up the apex of the ridge here. So this pinching, it kind of grows. It doesn't matter. Where it wants to grow, it will grow. Now, I did think that maybe some electromagnetic force was interacting here, and it was causing the synthesis of the iron on the ridges. But that doesn't follow the logic with it growing across the ridges and the valleys here. If it was the pinching effect itself, now it might be that the iron accentuates the pinching because of whatever reason. I don't know, but it doesn't make any sense that the iron formed at the same time as the ridge as I originally thought, because it goes over and under and over and under and over and here, and we don't see a ridge going in this direction. Okay, so this for me is a little bit like this Evos don't obey fluid flow laws either. And Ken Shoulders actually observed an Evo going through silicon carbide with aluminium, or as aluminium oxide or whatever, and he actually had aluminium oxide, or I think it was aluminium oxide or aluminium, but aluminium oxide I think it was, and it spread out, and he said up about an atom thick, extremely thin, and he had paraffin wax above it. So this was cold. It was doing this cold. It must have been superconducting and superfluid. Superconducting and superfluid. Just what you need to do some really cool exotic technologies. So I believe that we are we've been able to demonstrate with this sample superfluidity. We've been able to demonstrate exotic vacuum object shielding, and the fact that it had EVOs on it of various scales and so forth. I'm going to come back at some point to how the structure broke up, and maybe I will do that now. Okay, so I believe, let me just see if I've got any slides to walk through this. I've got any additional slides. So I believe that what you are seeing in this video that I presented some time ago, this is from a CIA document here, looking at John's materials, and you have some sort of wrench here. This is a rat tail file. So this is the rat tail file, I think. And you have north, south, I guess north, south, north, south, and then south. And then these two bits are south and south and south and south. And so when I saw these and what I observed in other systems, I assumed that a magnetic monopole was forming on here, and a magnetic monopole was forming here somewhere in the material, and it got so big that their fields interacted and there was just a yield strength and it broke. And I'm saying that what happens in the fracture sample is that the fracture sample may have something in there, and I originally said this to John a couple of years ago. What I think is happening is that in these samples, and I said it in the video where I referred to the rat tail file, that the EVOs were enveloping the structure as I've discussed here, and I believe that that is exactly what's going on. We've observed it, and Ken Shoulders says that's what happened. But before I read Ken Shoulders had said that's what happened, I'd observed it. And I believe that the long grains in here, we know from Matsumoto, and we know from Shishkin, and we know from Shoulders, but Matsumoto really nailed this, that the micro ball lightning, as he calls them, or itonic clusters, they congregate in the crystal grain boundaries, and then they start eating around, and then they form a something. Oh, I've just lost a bit. Okay, for the first question that gets answered, the person or finds an adequate explanation, they can either have a book or they can have this bit that just fell off this sample. This bit here. What I'm saying is it envelops a crystal grain until it gets one whole lump, and then the entire thing becomes one magnetic structure. It's one distorted electron, let's put it like that, or there is one that's so powerful in that piece that it's able to rip it apart from the rest of the crystal structure. Then when the whole thing starts to fracture, they realign to their respective crystal poles, and then when the music stops, they settle down. Because the EVOs are still churning material, they churn some of the material from an adjacent structure as the thing is dying down, and it ends up in a solid fractured state like this. And so I believe that that's how they're occurring. But what I'm going to show you in the latter part of this presentation is something that I found quite interesting, because it points to potentially the mechanism being quite a lot similar to what's observed with the rat tail file and the spanners and stuff like that just fracture. Okay, so I guess I don't want that slide there, so I'm going to move that down for a bit. No, I'm not going to. I'm going to. What I'm going to do is I'm going to show you a paper now. If it's here, is it here? Okay. I've got a slide that's out of order, so let me go down to that one, and I'll put that up there. Give me a second. Give me a second. Talk amongst yourselves. Okay. All right, I'm happy with that. Let's go. Okay. So what I'm showing you here is a paper that was published in article in Metallurgical and Materials Transactions A in November 2001. And what we are looking at here is a structure which is not too dissimilar from some of the fracture planes in the fracture sample. And here is a fracture that occurred at the top. So this is the top of a metal ingot, and it went in a little way. It went in a little way, and there's a close-up of it here. And it goes along the crystal grain boundaries, the dendritic boundaries. And here's the important thing, I think, here. As shown in figure 4, magnesium, silicon and copper tend to segregate in the last regions to solidify. The concentration of magnesium in liquid increases from 1 to about 8% when the solid fraction reaches 0.9. The silicon concentration increases from 0.3 to more than 4% in the last region to freeze. The copper concentration increases from 0.2 to more than 20% until Al7Cu2 Fe forms. The segregation of copper, silicon and magnesium significantly decreases the solidus temperature in the last region to solidify. These regions are usually dendrite or grain boundaries. Whoa, where am I going? Where hot tearing is expected to occur, as shown in figures 2 and 3. Okay, so this is figure 2. A surface crack shown in the middle of the figure with enlarged views at the top and the bottom indicating the surrounding microstructure. Note that the crack lies between dendrites or along grain boundaries. So the surface crack occurs along dendrite and grain boundaries. So here's the solid fraction. Calculated concentrations of solute elements in the interdendritic liquid during solidification of aluminium 3004 alloy. Copper, silicon and magnesium segregate in the last to liquefy, liquid to solid solidify. So what they're saying is that basically as the dendrites form, silicon comes out in the last region. And then you have iron here comes out, if there's any iron in there, last. And that would be within the interdendritic regions. Okay? So why is that important? Well, this could go some way to explain why you have these crystals. Are these crystals forming in the interdendritic region? Or is there a silicon oxide thing in there, and then that enables the production of the EVOs, potentially? And could it be, I'll actually show you the paper. Let me go there. Before I go on, let me show. This is the paper. And you can see this is 1/4 of a horizontal cross section of the cast aluminium ingot, and it's right on the surface. There's a little crack, right on the surface, a little crack. There's no cracks going through the body of the material, but through the body of the material, you can imagine that there is this alloy kind of between the crystal grains things going on. And so they're looking at this little top piece here and this little top piece here, A and B. And they've got it here. There's the crack that they're looking at. And they're saying that this particular alloy, 3004 alloy, has magnesium 1%, manganese 1.25%, silicon 0.3%, iron 0.7%, copper 0.2%, zinc 0.25%, and then the rest is aluminium. So it's basically, you would call this aluminium, and you would think that these aren't that significant. But what it's suggesting and is saying is the case is that as this solidifies, you end up with an increasing fraction in the intercrystal grain dendritic structure boundaries in the cooling mode that this went through. And so the amount of silicon goes up between the boundaries, and also it notes that the iron goes up in the boundaries. So how does this play into the observations of the fracture samples? Well, I believe that what is going on, therefore, is just like we see the kind of splintering here, but it's a much bigger effect. It needed for the material to get, the monopole or the pseudo monopole to get really, really big for this to split, and for these to split here. It needed to get really, really big for it to split. Then, actually, so before I go on, this is from the Hutchison file, and when I said to John, "Oh, I think this is what's going on," he said, "Oh yeah, George Hathaway thought something like that," and he sent me this Hutchison file, and it says, it's merely surface rippling some electromagnetic means. So it seems to be swirling, although it's not. It's merely surface rippling by some electromagnetic means. And the coffee cup is dancing around the top of a yellow milk carton. It's another way for him to determine where the zone is. Then we see a flat file, 8 inches, 20 centimeters long, breaking apart. The file broke into 4 or more less equal length sections. That's important, I believe. Normally, if you break a bar magnet, you know that you break it north-south, 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 etc. So the parts tend to stick back together again. In this case, the segments were magnetized the wrong way by some phenomena not known, and they repel each other when they're put together and at the breaks. This may be indicative of the development of large-scale monopolar regions that are of such intensity that they disrupt the material itself. It's as reasonable an explanation as I've been able to come up with, or anybody else. And so I'm always fascinated when you're not original, when you rediscover the wheel. So yeah, it was kind of like, okay, all right, there we go. So what I'm suggesting is that what you are seeing here going on with the rat tail file and this spanner or whatever is because the fraction of iron, and you will see there is some iron in this. Now, is some of the iron synthesized by the process? Could be. It does look like iron is readily made by Lena processes, and we have seen these iron oxide spheres, these aggregates, these bits of iron seemingly being synthesized. Well, if it's already got some iron in there, I would argue that that is, if you're making prima materia, or the mother of all matter, as Ken Shoulders called it, if you're making prima materia in the exotic vacuum objects when they're in a certain state, then when that wants to settle out and come back into our free space and be normal matter that we normally work with, it will see something that's like it's like a template for it to go to. So if there's iron in the material, you could have an increase in the production of iron, because that's the bit that the protomatter sees first. So, but anyway, there is iron, and you will see that. And we've already showed in previous things that you get what looks like superfluid, in my view. But if you can find, so let's do that as the first question, right? So I want people to see if they can find this kind of effect going on in some other system. Now, I understand that you might have a concentration of iron building up between crystal boundaries because it's got nowhere else to go. But how does something flow across the open surface of the material? So maybe someone can find something that would explain fully what we are seeing in these slides. And for the first person to find an adequate explanation that is just normal and mundane, they can have a choice of either the piece that's just broken off one of the Hutchison samples here, they can look at that in their own time, or a Space Earth human. Okay. So what I'm saying is that in the between the grains here, and if we look at our this backside here, you can see there are some cracks around here. Okay, there is a crack here. There's a crack here. Could it be that there's higher amounts of iron in here? Could it be that these pieces fractured because there was higher amounts of iron on the boundary? Okay. So what I'm saying, therefore, is that perhaps iron concentration at grain boundaries increases. So that is where the magnetic monopoles aggregate. As they get stronger, they cause fracturing and then realignment because there is some matter captured into the coherent matter. This can then come out and fuse the metal together. Drawn aluminium alloys will tend to splinter like wood and rearrange. Different composition aluminium with small grains or pure aluminium may go more jelly-like and allow fingers to be imprinted. So I'll share some beautiful images, but I've already shared some in my Steemit blog where Alec Pizarro was working with John Hutchison, and he turned off the equipment, and Alec went into the active area and went to pick up a piece of aluminium that had been jiggling around, and he was able to put his fingers in and leave his fingerprint in his actual print in the aluminium. And I believe that that probably was a much more pure aluminium. If it wasn't a pure aluminium, I'm arguing that because of the way aluminium ingots form, and you get drawn or extruded aluminium and you get these long crystal grains, that the iron concentration or the paramagnetic elements are on the boundary, the higher levels of paramagnetic elements. That is where the magnetic monopoles cluster. They tend to like to go to, the EVOs tend to like to go to, or the itonic clusters or microball lightning like to go to crystal grain boundaries. But in this case, they can align with their magnetic structures, form that skin that we've seen in, I've gone through examples of, and that Ken Shoulders said is what happens, and we've observed it. And then that whole structure has its pole in one direction because it has to, because it's coherent matter, as in the Salvatore Pai US Navy pattern, which I believe is a derivation of the work from the 1950s and what was obvious from that, and what Ken Shoulders had in his pattern. And so you have that, and that this particular grain here, this one here, that's off at this angle, this had coherent matter around it, and the whole thing had one pole. Okay? And another one had another pole, and so when the music stopped and they were all broken apart, they all arranged themselves, and then when it settled down, they fused themselves back together into this splintered pile here. And that, I believe, is how that occurred. Does anyone have any questions at this point before we start on the elemental maps? Anyone have any questions? Hi Shockwave, hi Bestow Primer, hi Ron. So Ron says, Bob, this is very interesting regarding the differences in aluminium. I've witnessed melted and res heat sinks of... Okay. So in the case of the aluminium that Alec Pizarro picked up and left his fingers marks in, I would imagine that was quite pure. It didn't have a lot of admixtures or alloying elements, and so the effect was on the surface, but it could build and build and build on the surface. And so basically he was able to squish his fingers in to the degree that was possible with the level of the exotic vacuum object skin that's on there. Let me find a picture of that for you so that those that may not be familiar with that example can have an idea of what I'm blathering on about. So I've got a picture here. So I've got this thing on Steam at Homo Symbian called The Challenge of Containing the Active Agent in Low Energy Nuclear Reactions. And I'm talking about the need to bleed, or you can build and make and break them, and so on. The challenge with metals. I said when using any metal that gets exposed to the active agent, it will appear to liquefy, not melt, based on its conductivity, ability to transport the active agent. Melting point, well, I guess we can all know what the active agent is now, but there are a family of things, but they're all at the root level very similar. Susceptibility to failure, electron lattice bonding, and electron affinity, desire to take on board the active agent, and other factors such as possible net energy gain from fusion of nuclei. So here is the sample that I'm talking about, and you can see that there's this kind of like jigging going on around here, but you've got the fingers pushing into this, and it basically kind of slipped from his hands a bit. I don't know if I have any more. I've got some other images of that from different angles, and you will see those. Okay, so that's what I'm talking about in this case, and you can see this didn't splinter. This didn't splinter in the same way that the ones that I've been showing you did. And apparently Alec Pizarro said it was cool to the touch. When he touched it, the implication is that it's cooler than the ambient environment, and I would expect that to be the case. The other thing is, I considered, could he have got a piece of wood and cast aluminium into the wood? And when you look at whether that's possible, and also there are samples of wood being inside aluminium. Now, if you can imagine, the aluminium has the EVOs on the outside, and a piece of wood is on top. It could be the case that the EVOs are kind of like envelop the wood sinks in and it pushes the EVOs further down, so it actually goes inside. And this is what I'm saying is, if you had a ferrous based metal, an iron based metal, the EVOs could skin that and it would then drop into the aluminium. And so he observed that kind of thing going on. But I've got a video here actually where this guy is trying to cast aluminium into wood of various different types, and essentially they all burn. They all burn, and they look very, very burnt. Very, very quickly they burn, and so it's not surprising because of the difference, the ignition temperature of cellulose and the temperature of melting of aluminium. But essentially, you're not going to be able to get wood inside aluminium easily, and I don't think you're going to be able to cast something that looks like splintered wood. You could do some sort of investment inverse casting where you do an inverse, then you do a positive, then you do an inverse, and then you whatever. There might be a way, but I would expect to see. I would expect it to be extremely difficult to cast this. I mean, just really difficult. just nigh on impossible, and this too. So yeah, I don't think that is going to be plausible. Okay. All right. Is there any metal that would not go to a liquid? Tungsten? Tungsten just doesn't do anything, doesn't do anything, doesn't do anything, and does everything. It's very conductive. It's paramagnetic, and the EVOs will aggregate on it, and at some point you get to a point where the transition between non-coherent tungsten loaded with a lot of EVOs and the whole thing being coherent is like that. and at that point, the EVOs just eat the tungsten for breakfast. And so we've observed that in Vega experiments. It was observed by David Hudson. It was observed in the 1980s. It was observed by Tadahiko Mizuno in, I think, 1994. And I think Sapphire recently observed it as well. But I think the credit should go to Irving Langmuir, the inventor of the tungsten filament light bulb. I believe he observed this phenomena in the 1910s. Peter Munger talk about it. Oh yeah, so you're talking. Yeah, I did a presentation some time back on Steemit. That I mentioned it at the beginning. You weren't here, Shockwave, but it's on the MFMP Steemit, and it was a few years back, and I was basically saying that a lot of EVOs are due to ball lightning. I called the presentation UFOs over Hessdalen, Norway explain ball lightning and low energy nuclear reactions. So natural plasma balls and LENR fireball phenomena in Hessdalen, Norway. And so it's a long article, and you've got the spiral structures that we've been creating in the Vega experiments. Oh dear, soon this is all going to be very boring. Oh dear. And I talked about these iron oxide, these magnetite balls, and where we've observed them before and where they've been observed before, and in our experiments, in the LENR field. And I said, and using that, I predicted that we would find them in the ultra experiments, and we did, unless it's contamination, which is possible too. But I think it's being synthesized. Let's put it like that. Okay, so I'm going to go on to the next part of the presentation. Resonance is everything. You said residence is everything, but I think you mean resonance. Okay, so I'm going to go on, and this is another part of the presentations I've shared in the past, and this is another area of the fracture sample. And what I think is amazing about this part is you have this kind of like pin, what do you call it, a quilted cushion thing going on, and you have a structure here with a hole and a sort of pletra shaped thing here with these stretch bands coming off. And you have these stretch bands coming off here with another pletra shaped here with a straight line across and something that's off frame, which I didn't capture. And then you have this other thing that's wetted into this valley and an object down here, which may or may not be detritus. And then you have this definite sort of field here and then field going at 90 degrees to it. And then within that, you have these little spots. Now, could these spots be something to do with the field structure? Maybe. Could they be to do with the tips of some crystal grains? Maybe that could be that too. But what do we see when we look at this? Well, these are the arrangement of magnesium. And so if I play this, that's the aluminium and that is the silicon. And when you look at this up close, the magnesium is on the outside. So if I go back here, I can show you the magnesium here. They have these rings of magnesium, and then right in the center you have the silicon. And so aluminium is either side, sorry, silicon is heavier and has mostly bosonic isotopes, and the same for magnesium. They're mostly bosonic isotopes, but they are lighter, and aluminium is fermionic and it's in the center. So if you were going to compress 4 atoms of aluminium into 4 other atoms and make them all bosons to occupy less space-time and give you a lot of energy, you would do the sharing of nucleons to end up with silicon and magnesium, and the silicon is in the center. So this kind of would be a structure that could be formed by some type of compression, and that is the silicon, I believe, on the surface. Where's the silicon? Where is silicon? There, silicon. And now we're going to talk about this structure and this structure and these structures, and what is really interesting about that. So you can go and see a presentation that I've talked about this before. And I think we got 2 more videos here. So just these are talking about the spatial arrangement of these. So I did a video about this and about their distance and so forth, but this is kind of similar to what I'm talking about with the coating that is on the inside of the jewel and that's on the overall outside of the fracture sample, and how they may or may not be arranging themselves. Okay, but this is more interesting to me because something very bizarre is going on. Now, I've talked a little bit about the iron in the material, and you know, and given a hypothesis that iron and silicon may migrate to grain boundaries. But what we're seeing here is something that's really rather bizarre. If you go back to the where is it? Here, up in this top corner, you've got the plectrum that I was talking about, and you've got another one down here. I'm going to zoom into this section here and this section here. Not in that one, in here. So those are the 2 areas. And note that they're basically 90 degrees from each other, except this one is kind of like the flat area is pointing up, and in this one the flat area is pointing down. Okay? And the really interesting thing is that the silicon, these plectra-shaped pieces, they are silicon and calcium. Okay, on one side. The flat with the slight curve is silicon and calcium. The long one here is less silicon, but silicon and iron. But there is absolutely 0 iron here, and there is 0 iron here. In these pieces here, there's no iron. You can see no iron there, no iron there. The other interesting thing is this chip that's in the valley is iron and oxygen. Iron and oxygen. So this is iron and oxygen. These are silicon and iron with no calcium and oxygen. And these are silicon and calcium with no iron or oxygen. Now, is this some sort of phase interference? It looks like we have intersecting frequencies here. You've got one large frequency here, the same kind of frequency going that way. And then you have these smaller frequencies doing these things. Is that what might be causing this? Why is this particular shape around the whole silicon and calcium with no iron or oxygen, and the same here? But it's at 90 degrees to it, basically, essentially. Silicon, calcium, no iron or oxygen. And then the thing on the other side. Now, when I first saw this, I thought maybe this is unique. Maybe it's just this area. Maybe it's just this area. That's not the case. And I would like someone, and this is the second question, as to why Can you explain? And this is going to be related to the extra data that I will share at the end. You couldn't see the iron picture? What do you mean? Down here, it's in the bottom right. Oh, you couldn't see the iron picture because I'm covering it up with my stupid mug. Right. Okay. So, right. Thank you for that, Artlevan 1. Right. So, this piece here is iron. Here, iron, and this is iron. It's iron and oxygen here, and this is iron without any oxygen. Iron and oxygen, iron without any oxygen. It's totally bizarre. But the iron has silicon, but this iron has no silicon. Now, this and this have silicon, and this have calcium. So one side has silicon and calcium with no iron or oxygen, and the other side has silicon and iron with no calcium and oxygen. And then this one has iron and oxygen with no calcium and silicon. What's going on? And these notes here, they shouldn't actually be there. I was just putting them in there because I was trying to think of some way as to explain this. This is diamagnetic and ferromagnetic. And this is ferromagnetic here, iron, and paramagnetic, oxygen being paramagnetic. So could it be some sort of a magnetic relationship? I don't know. So it's some spin. What's going on? What's going on? Why have these flat ones? This is a flat one and a flat one with a slight curve and a slight curve. Why do those two have silicon and calcium, silicon and calcium, but no oxygen? Neither of them. Why does this one have iron and silicon but no oxygen? And why does anyway, so if someone can explain this and the data that I'm going to show at the end, they can also have a chance to grab one of these books, because I want to see if that is if that's explainable in another way. So I kind of listed down the elements here that we've got and said, like, you know, we have a tool on the Nanosoft MFMP's package. I asked a couple of Christmases ago for this to be added in, and if you go there, you can choose an element and it will tell you how diamagnetic and how paramagnetic and how ferromagnetic it is. And so you've got the elements here that are observed and carbon, oxygen, so on. So, but it doesn't really explain it. So I kind of want someone to see if they can come up with an adequate explanation for what's going on here. Now, the rest of this presentation is going to be a little bit sloppy, if it hasn't been sloppy enough already, because I didn't get the slides done. So if you just bear with me, talk amongst yourself. Because this is really rather special, what I'm going to share with you now. And it is just, in my view, a little bit of magic. So I'm just going to show you this, which again, this is the image from that 2001 paper, and this is a segment from the fracture sample. And so you have these lumpy bits, which are, I would imagine, interfering structures. So they're not too dissimilar from this. Within this particular structure, though, you have these lumps, and we've seen that these lumps are like magnesium and silicon. And it has kind of like these stretch marks all over it. What are the stretch marks? Because I don't see the stretch marks here, but it might be the resolution that this was taken at, or it might be the particular elements involved. But there's a type of stretch mark which is quite interesting, which I want to share with you now, and it's from Stone Ridge Engineering, and this is their small coin process, and it's not a new thing. It's been known a very long time. You can shrink coins using a Z-pinch, and you get a very high charged capacitor bank, and then you discharge it through a coil, and it just immediately shrinks a coin. But it has this kind of effect, and I quite like this, because if you look at this, the coin, look at where this the first state is here for Delaware. Ah, lovely Delaware. The first state here. Now look where the S is here, and in relation to the coin horse there. Now look, the S appears to basically have gone underneath it. Isn't that bizarre? So this is using 5,000 joules in a capacitor, and you have 1 or 2 coils or something of copper around the coin, and you just blow up the copper coin. Blow up the put all the discharge through the coil, and it produces a pinch, and the pinch induces current in the coin, and it squishes the coin. But I think what's very interesting is the displacement of the letters, so that they move basically underneath the horse. They actually have on this site, I don't know if I can find it, they have all kinds of coins. They got some examples, but there's a square coin, and it looks like a cross section of John Hutchison's metal bar. The interesting thing is here that the volume is supposed to not change, because it just gets fatter. Okay, so but it has these lines on it, and these lines are a very specific type of thing. And they're called Luda Bands. Here, Luda Band. And this is on aluminium magnesium alloy sheets. And what they've done here is they've got a device here to stretch an alloy. And then you get these things called Luda Bands going on in the metal. And it's kind of like the I guess the intercrystal boundaries of slightly different elemental composition, and then they slip, and it's one of the modes of failure of buildings and stuff, or metals generally, structural metals. Here's some other imagery about Luda bands. You've got a boundary here, and you get some thinning going on here. Like you can see some thinning, some necking going on. So is it that these are Luda bands? I don't know. There's not so much stretching as squashing. I would be interested to see if there's any elemental shifts going on in here. To get one of these coins, like cut it in half, or cut a hole out of it and do its elemental composition, and then get it shrunk by these guys, and then dissolve it in acid and do an ICP-MS on the remainder to see if there's any change. But I think that was just an interesting thing to put in there at this point. Get that out of the way. Okay, give me a second. So, this is quite an interesting artifact here. And why I'm saying that is because this particular agglomeration of whatever it is seems to have moved across here. This is normally carbon, if it's looking like this smokiness here. But it seems to have left this trail of the iron stuff behind it. Now, could this have been in an exotic vacuum object? It does look a little bit circular, maybe. This detritus over here looks like to be the same kind of rubbish that's over here. Is this synthesized material? Is this just fragments of dust or whatever? I don't know. But why I found this interesting is that this looks like it has left this trail. And we know from the other examples that this is this iron. I don't think this came out of here because the growing direction has a spike on it. So this looks like a sword up here. This is growing in this direction. And so I think that maybe this had a lot of this superfluid material in it. And as it went across the surface, it was like a bit of a slug and it left it behind it. So I just thought I'd put that in there and ask people what they think about that. Bob, if you want, we could shrink different metal discs for you. Well, thank you. Join the technicians. You know, it's very interesting because you are going to be exploding a wire. And what does an exploding wire do? It produces exotic vacuum objects. So now these things are electronic objects that can cluster and form at electronic speeds. So are you effectively creating a scenario where it's not just the pinch, you actually have an Evo that's there and you're making and breaking it at the same time? I mean, yeah, you are crushing it, but normally you blow up. Yes, Michael Claridge, Langmuir is the first. Good to see you here, by the way. Excellent. Thank you for joining us. It is crushing, but I don't think it is just crushing because you will have a scenario where there are some EVOs. Because if you remember, strange radiation was first, although Matsumoto saw it first and so did Solin see it first. The first person to give it the name was Leonid Oretskev, and he blew up titanium and other foils in a water chamber in polymer in metal, and he ended up by producing ball lightning outside of the structure. So when you blow up these things with these high current discharges, you tend to get something that looks a little bit flashy, and you may be producing quite a lot of strange radiation. So if you've already got that equipment, I would suggest you get yourself some X-rays films like these. They're about $35 from, I think they actually come from India because they still use them. They're self-developing. Or you can use some like 100, 200 ASA black and white film and have it in the roll. Just leave it in the roll and you put that in the vicinity. Or a webcam like this and you mask that with PTFE tape. I think the PTFE activates the strange radiation. So there's various ways to maybe look at that. So that would be very, very cool. Okay, so I'm going to go now try and show you something which, to me, it just absolutely boggles the mind. And I still need to finish the slide first, so bear with me. I'm going to be manipulating some images and all kinds of gubbins here. So, that's just amazing. It's just amazing. You're going to love it. I'd love to know what it is. Love to know what it is. So when I say it's two things, it's kind of like a whole group of things, and it's in a field on the sample. Okay. This is good enough. Okay, well, I'm going to fiddle around with this in Photoshop, but you'll get the idea. Okay. Right. So I'm going to give the money shots first, and then I'm going to show the contextual shots. So what we've got here, when I've got the mouse on the right computer, is what I call the bridge. This thing here, the bridge, and the hole. The bridge and the hole. Now notice what you see in this hole. You see one of these these sharp-edged structures with the curve on it, and then something coming out. Something coming out. Okay. And then over here we've got a sphere. And then we've got one of these agglomerations that I've just showed you with some sort of stuff coming out of it over here. We've got another bridge over here, and this one you can see is spiraling. It's spiraling from here. It's like two sides, and it's spiraling from a point up here over to a point down here. Now remember what I've been saying about lighter things in the field. Okay, if you have a heavier element, it will be lighter generally. So what you're seeing here is the aluminium here, and then as it goes across the bridge and it goes into the center of the bridge, it gets lighter and lighter. Okay, why is that important? Well, maybe we'll find out. And then there seems to be, from the center of the bridge, there seems to be something flowing down and flowing down. It doesn't matter whether it's going over ridges or going up a hill. It doesn't matter whether it's going up a hill. It's flowing down, it's flowing down, flowing down. It kind of ends up down here. Okay? This, when you see it in whatever else I'm going to show you, it's kind of vortical. There's kind of like a crisscrossy thing coming off this way. Look, you can see it goes round there, goes round there. And then you have these kind of pinch lines coming in here. Now I'm going to show you the whole field of the material here because it's quite beautiful. And it's actually part of this is what you saw on the title slide for this presentation. So let me get that for you because it's a very large image. Okay. Okay, so here we go. This is our part of the fracture sample. In fact, I've got a more taken out shot than that. Before we go in there, I'm pretty sure I've got a very wide shot. Is it this one? Is it this one? Not sure it's that one. Bear with me. Oh, well, that'll do. We'll go back there. Okay. So the hole and the bridge are actually quite close to each other. So we come over here. This is the bridge over here with our sphere. We've got another hole here with something poking out, which is quite amusing. And then we have this structure here with our vortical hole with the material going down, and we'll need to look at a higher resolution. Now this isn't the only place you've got this. Look, we've got another hole here, and from one side of the hole You get a flat side, and then materials. Well, actually, this is if we use the same logic, our direction of flow is this way. Our direction of flow is this way. Is it that way? Oh God, it's difficult to tell on that one. But in this case, from the bottom here of this, and bearing in mind this is down in a hole, there's something flowing out. Is it flowing to, or is it flowing out? You will have all these. I mean, this looks like it's flowing in this direction. And it doesn't matter whether they're going over ridges or whatever. It's just flowing. It's just flowing wherever it goes. You might think it's going in a valley up here, and it might be going in a valley. But for some reason, it decides to get to here, and it goes up and down and up and down and up and down and up and down over there. And this is iron. It's flowing. The iron is flowing around on the aluminium and leaving these thin crystallite structures. It's absolutely fascinating. But what's more fascinating is what's going on in this hole and around this hole. And what's more fascinating is what's going on in this bridge. Okay? And what's going on when it comes down and comes over here. So that's context of that. And you can have these pinch points like down here. Like there's a pinch point here, but it doesn't seem to do anything. Okay? And there are, this material, this stuff is flowing. I mean, look over here. It looks like there's a little hole here, and all of this material is flowing out. Is it flowing out? Yeah, I think so. What is it? What is it? And it's not the only places you're going to see these. I have other shots. Like I say, when I showed you before, it's not a one-off. It is not a one-off. Here's another one. You can see this serious pinch hole here, and the carbon blob on their side. But here's one, and it's just got this kind of flower at the end here in this pit. And here's a nucleation point, and this actually, we won't do with this today, but this is actually a copper flower. It's a copper flower, and from it, this gargantuan structure emerges with these spider webs of magnesium threads on like diamond structure. But it's very similar to the spider structure. But let's go back to the features we came to see. Now, we've seen these kind of structures before. Maybe I can show you in here. It's in here. This is in line as well, if you recall. And we have a north pole here and a south pole here. And if I press play on there, you can see the north and the south. And I've got it magnified. Oh, no, I didn't want to do that. North and the south. So we have our north little cannon up here, shooting stuff over to the south, and when the music stopped, the stuff that was inside it, that was being ejected, kind of came back into our universe. And we have a north and a south here, we have a north and a south there, and we have a north and a south there, and I just mapped through those. So north, south, north, south. So these are... This is up, down. This is across a valley. So this is actually like formerly two pieces of wire, and it's going from one side to the other. This is kind of like across a little bit. This is more at a softer angle to the ground. But what I'm showing you is that these things can shoot nearly horizontally from north to south, or vertically, perpendicular to the surface. Okay. So we've seen these kind of structures before in Lion. And that is effectively what I'm saying we are seeing in the this structure here, which is what we're going to address first. Okay. Now, is this the south or this the south? I don't know. One or the other. And what I've done here in the software, in Alan Goldwater, MFMP Volunteers Lab, Magic Sound Lab in Santa Cruz in California, is I've drawn a line from here to here to see how the elements shift as I go over there. And you've got all the elements down the bottom here. And you can see some sort of twisting going on. Not quite as clear as the twist that goes across on this bridge, but I'm focused on this bridge for a reason. You'll see why in a minute. And as we go across to the center, I'm highlighting here the copper peaks at, just beyond the center. And this green one that goes up like a rocket is the iron. So there's an huge iron peak right at the center here. Okay. In this shot, I am looking at the oxygen, which is off center. So over here, we've got more oxygen. And it's a coincident with chlorine, with the oxygen. And the magnesium is pulsing up and down, pulsing up and down, and pulsing up and down. And that kind of follows the white areas here. And so this is a bit like when we saw on the spider web and the one that I just showed you, where the lighter areas on these tend to be the magnesium, and I think probably carbon, if it's there, if you could see it. Maybe I'll go back to the previous slide. Is the carbon here? Well, the carbon's over more on this side. In fact, the carbon ramps up. I don't know if you can see that down there. The carbon is ramping up, but it has a peak somewhere over here, and probably where this blob is here. That might be the port, the exit port, but anyway. So something happens in the center here, and I think that these are my models for our EVOs, and they're acting as north and south monopoles, and they can form a flux loop. But where they meet in the center, you know, it's got a bit of a conflict going on. And here's a hydrodynamic model. This is an aerofoil in a dusty tank in water, and they've just moved it across, and they've just shown how the vortex flows go around. And this is how you see these structures. And I remember early on I was talking about how these things intersect. Well, the full radius there intersects with the center of that one. The full radius here intersects with the center of this one. And the half radius goes halfway between. And so that's why you end up with these kind of structures that I'm showing you here, where this is like half the distance, and then the full distance of this part goes to the center. So so I'm suggesting that what you're seeing in this structure across here is a flux loop, but we're now going to look at all the material here, and this is going to get a little bit sloppy because I'm going to go into the raw data, and I'm sure that's not going to bother you at all. I just need to find the right one. Okay, hopefully this is visible for you. Okay, that's not going to be helpful, is it? Let me do that. Sorry, if I had more time, you wouldn't have to been waiting. You can wait as I do it. Okay. Okay, first up, I'm just going to read this to you as I see it. So this is an overall look at the area. We're going to dive in a little bit closer. So what do we see? This is atomic concentration. So remember, when you're looking at atomic concentration, iron and calcium are much heavier than carbon and oxygen. So the weight of something at 2.99 is much higher than it would appear based on just looking at the percentage atomic concentrations. Okay, so let's have a look at what we're seeing here. So let's have a look at the center of fracture 879. So that's 879. That is largely carbon by atoms. It has oxygen, magnesium, aluminium, and quite a high concentration of iron relative to everything else in that center point. 876, where's 876? 876 is this agglomeration that we saw one leaving a slug trail earlier, similar type structure. And this is in this pit. It doesn't look like that this was detritus. It's something going on with what happened overall, in my view. And this has 2.99% iron, and it has silicon in it. The sphere 875 has high concentration of silicon relative to anything else. And so 875 and 876 both have silicon in them. Nothing else has silicon in them. And they both have iron in them, and they are the highest and third highest concentrations, other than the center point here. The hull we can't really see into. What does the hull say? It's got a bit of iron. You can't really see into it. The counts are probably low there. Fracture 882. Okay, so that's got no iron, but that is basically aluminium with a bit of magnesium. This 881 up here is the highest concentration of carbon. Okay? Virtually no iron, virtually nothing else. There's a bit of aluminium. Now, I believe that this is almost like a diamond. Okay? Because it's probably that you're looking through, and the photons are coming back from the aluminium underneath. And so you're seeing more aluminium than you should do, and this is maybe diamond. It certainly has very sharp faces to it. Okay, so that's that, but we're going to go into much more depth on this. Okay. So here we've got the bridge, and yellow is silicon, carbon. So carbon's down this end, okay? Silicon appears to be going across the whole way, and then there's iron. And it looks like from the center, you actually have a flow of material, and it comes down, and as I said when I was looking at the SEM, it's going uphill and downhill, coming downhill here. It's going all the way over, and it kind of goes left and right. It's almost like this ball was rolling left and right and left and right, and it comes to here, and there seems to be some separation going on. There's a slug trail over here, And you have mostly iron on this side and mostly silicon on this side, but there is some silicon in here, as we showed from the previous data. But it's almost like where I'm showing you in this image here, where the center point is, maybe they're two of the same pole or for some reason, but whatever, where the center point is, or where the interaction between these two things are, you're getting something bleeding out of the flux tube, the magnetic flux tube. It's bleeding out of this center point. Let me zoom into that so maybe I can get you a better idea. Maybe you can see that more clearly. So here, this is the bridge, and from the center point, you've got silicon and iron bleeding out, and it's coming down here, and then you've got the sphere and the agglomeration, the sphere and the agglomeration. Now, again, I remind you that it was the agglomeration from which we saw this slug trail of iron going across the surface of the aluminium. Okay? Let's see what we got next. We'll look at this one. Okay, so again, interestingly, from the center of this, when you look at, I think it's the copper here, the copper is coming out of the center point, and it's coming down, and it's going mostly to the sphere side. Absolutely bizarre. The carbon. Okay, so I've got some point markers across here. Okay, this is obviously a different structure I'm looking at. I don't know where that structure is. Yeah, so this is this one here is, I thought this might be two playing together, two structures playing together and making the overall heart. It's not the heart shape, but it's got the pinch point in here. So I just looked at this because I thought it was interesting. This isn't part of the overall story. I'm showing you here, but it does seem to think it's got tellurium, but I don't think it's tellurium. I think it's probably a band overlap, so let's not dwell on that. I need to go into the ball there, so I need to get up a different image now. Ay, ay, ay. Where are you? Okay. Okay, I've got some image maps here. I don't know where the PDF for that's gone. Let me just have a look again here. Talk amongst yourselves. Where's everyone from today? Okay, don't think I see anything more in there. Okay, I'm going to go through a bunch of images now. So the way to read these is, I've talked about this before, where you see something that's everywhere, it's probably nowhere. Although we do know we see some silver in here. So let me just get this into an array that I can show you. Okay. So silver seems to be everywhere, so it's probably nowhere, but we do know there is some silver in the concentration there. Aluminium is very marked, so that probably does mean that the aluminium really is there. And you can see that there are spots where there are nothing. Here on carbon, you can see it's the bridge is, and this bridge up here, and by the way, these are parallel. There might be something in that with the field structures in the overall affected material. But the carbon is 100% in that entire bridge. And you can also see a flux coming down here and lines coming in. So this definitely looks like the one that's feeding the carbon in, as it were. And you can also see over here, there's a spiral at the end here and a spiral at the end here. We'll talk about this maybe another time in more detail, but there's quite a bit of carbon on the whole side here, where that structure is over there, but we're going to look at that in more detail. In terms of calcium, there's calcium in the silicon ball there, but nothing really in the iron. In terms of chlorine, there's a couple of concentrated areas. There does appear to be some chlorine in the flux loop between here and here, and maybe something coming down towards the ball. Here you can see in the copper very, very clearly. If I go back to the image here, this is the image of the bridge going across the whole way there. And from halfway, I don't know if I can go back to the copper image. I'll leave my mouse there so you can see that that's the halfway point. The copper only comes to the halfway point and then it bleeds out down to the sphere. I'm going to put that back there and I'm going to go back down to the SEM. So the halfway point, you see the bleed out comes from the halfway point and the copper comes down. I think you'll see the same thing, only more intensely, from the iron, if I can get that. There's the iron. Now look at the iron. It's so striking. The iron comes from this side to the center. It's most intense in the center and it bleeds down. And as it comes down here, it gets very intense here. And then it's not in the sphere at all. But it comes down here and ends up in this conglomeration here. This is just so bizarre. It's so bizarre. But look at what you're seeing over here. It's like the peanut guy from Ghostbusters. There's iron ridges around the outside area of this structure that's over the hole. And then you have this bleed out from there that goes into this overall structure that goes superfluidly over the whole of the surface above, as we showed earlier. You see the hole with the vortex going down here? Is this aluminium converted into material? Like 2 aluminiums go to iron 54. Or if you take combinations of magnesium and silicon and so on, you can end up by getting other isotopes of iron. And so, is this iron being synthesized by this? Why is it only on one side? Is this tail here the down part of the, how should we put this? Is it the down part of the ankh? Is this circle piece here? Is this the area where the material is consumed? Are these wings the 2 side arms of the ankh? Who can say? But let's go back to this structure here. So here you've got oxygen. Oxygen goes all the way across and there's oxygen on the silicon. So this ball is silicon and oxygen. This looks like it is quartz. It's a synthesized sphere of quartz, and we actually saw silicon and stuff being formed in the microwave reactor Nova in 2017. See where that is. Okay. Look how striking the silicon is. Silicon, oxygen, silicon, oxygen, silicon, oxygen. And look at the silicon here. Again, the silicon seems to come from the pipe. There's there's a bit there, but it's like everywhere. But it comes from here and it goes down here and it gets very intense. It's like has a pole here. It comes down to a point. Was this structure much smaller and then it just came into our 3 space much bigger? Titanium, there's just a few blobs. It's everywhere, so it's nowhere. There's a bit of zinc in this area here, which is not surprising. If you have copper coming down, zinc is like 1 proton away, so you would imagine. But it's really a very small signal. Tin as well. There appears to be a very small signal of tin. Tin's very heavy for that to be there, but essentially it's everywhere, so I wouldn't really give too much credence to that. It's these kickers of the silicon on this slug trail here of the iron is absolutely killer, but it only goes over to here. It comes down on the same slug trail, the same slug trail that you see the where is it, the copper on here, the same slug trail. Absolutely amazing, absolutely amazing. So I'm going to put these into the blog, but what I have to share you now is actually what's going on in the hole when we take a deeper look at the one side, the side that we are looking at here with this very strong iron signal here. And the material coming out. We're going to have a deeper look on that. So let me just grab something and put it into Photoshop so I can show you the 3D nature of this structure with a little bit more clarity. And this to me is, it's just mind-bending. It really is. It's just mind-bending. Okay. Come on. Photoshop's not liking the color space. Okay. I've dealt with you already. Okay, first off, we're going to have a look at just the hole on its own, and then we'll have a just to see the depth of the structure, and then we'll have a look at the elements and so forth. Okay. So here's our hole, and I'm just going to play with the levels here so you can get a better idea of the depth of the structure, because certain views in an SEM reveal structure and others reveal elements more than structure. So if I can pull that down now, I think you can get an impression here of how deep this hole is. It is very round. It possibly has some slightly polygonal nature on the inside. When you look at the elements, you can see the vorticity appears to be going down like this. There's pinching going in here. There's pinching going down here a little, but it ends up being a little bit smoothed around the actual hole here. And then this one is actually split slightly off-centered. And you can imagine that maybe there was an original one that formed, and then as it went into the surface more, this came up later. But whatever, these structures on here are not nothing, which is special in its own right. So hopefully you can get an appreciation for the kind of depth of this hole. I'm going to find the next image I wanted to share with you. So this is the wide shot. And it may be clearer to you, the kind of vortex nature. So it's starting here, it's going down, and it's going down. Okay? Okay? And you've got the stretching going in, Okay? And you can see the thing coming out here and then going over ridges, and then comes up here. And then starts to bleed out. You can very, very clearly see it's going over the ridge. It really doesn't care. It doesn't care. It just wants to go in that direction. Again, it's going over ridges here, going over many, many ridges. This sample, I think, was made in 2007. 2007. Okay. And it's almost like these black splodges, which is a different element, probably silicon or magnesium. They get more densely packed as we come into the core here. This is our kind of diamondy structure up here. And if I go to the right now, literally, you see this structure up here. It's a similar kind of thing, but there isn't a pit that goes into a hole with a cavity. This is the same one here, but you can see you still have a flat thing here. So you can imagine that this is the start of one of these. It's an earlier one, and it's got a flat head to it at this time, and it goes down to a point, and then it's got some flow coming out the backside there. Okay. Now, we're going to start looking at this in extreme detail. So we're really coming in here to the base of it. That's about the limit, 8,000 times on Allen's microscope. But the overall structure here, I guess, is about 20 microns across. Now, my question is this something similar to what I was showing here? This is from the synthetic electromagnetic knot in a three-dimensional skyrmion. And is the hole something like this? And is this hard line here, this hard line here, this hard line here? And is what we see in that little plectrum, this pinched area, something to do with what goes down here? And I showed, if you remember, other examples where the sphere is eaten out of the carbon, the diamond in the Lion reactor. There's a tail coming out of it, and the tail is a heavier element. Okay, the carbon is 12, and the tail is a heavier element. In the case of the Parkhomov reactor, there's a sphere taken out of the aluminium oxide, and there are spheres of iron that have been deposited in a cone. And if you actually look at some old texts of what ball lightning looks like, you have a ball lightning and then there is a tail, like a trail, a comet trail behind. And I would imagine that that comet trail will have heavier elements that are in the ball. It's kind of like, as it's eating the air in front of it, that it's being condensed down, some of it will be synthesized into heavier elements, and it spews it out the back. So is that what we're seeing here? There's something coming out here. I don't know. This obviously is extremely small. It's only in the thousands of whatever atoms they were using, probably cesium. And this is very, very large. But this has the hole in it. Is it something like this that we are seeing when we are looking at this? And it's just effectively rotated round the other way. Okay. So I'm going to go in and look at the elements here, and then I'm going to look at the elements that change as we do line samples over here. So let's have a look at the first one here. This is silver. It's probably not a lot of silver in there. It's everywhere. You can't see very much into the hole. So where we're looking here into the hole, the electron beam from the scanning electron microscope can't get in. So it's not surprising it can't see much there. So it's saying it's silver, but I don't think there's much silver there. There might be some. Aluminium, well, that's not surprising. Is this an aluminium glass? Is this sapphire? Don't know. There's a lot of carbon. Now look where the carbon is. The carbon is on the edges and on, well, have a look. Is it that one? I'm trying to find the matched image. Where's the matched image? There. So we have carbon on the edges. And interestingly, aluminium goes in and out of phase. In and out of phase. So the aluminium is more here and the carbon's more here. Is that right? No, carbon more on the edge. And this is where it starts to get really interesting. Calcium, maybe calcium there. Chlorine, no. There does look like there's copper. There's copper, and look where the copper is. The copper is in this whiter area, and that's what you would expect because it's the brighter thing here. So you've got a little bit of increase in copper there. Okay. Now this is fascinating. This is intense. So where the copper is, you get the iron. That's kind of what we saw in the bridge when you look at the slug trail. Yeah, you got the copper and the iron going down from the center of the bridge, bleeding out. Okay. Now, is this a north and a south that are both in the same location, and therefore you can't see it, can you? Sorry. Sorry about that. Okay. All right, let's start again. Silver. Silver here. I've got to get better at that. I need a different window which is showing me what you're seeing. Silver, not really there. This is the aluminium. You should imagine there should be some aluminium there. It's everywhere. The carbon here is on the edge. Look at the edge here. You're seeing the carbon. Okay. Where do we go? Look at the iron. The iron here is intense. Compare that to the SEM. Compare that to the iron. Compare that to the SEM. Now look at the iron compared to the copper. It's kind of co-located, but the copper signal is much weaker. But this is basically what we saw on the bleed out from where the flux loop met. And what I'm suggesting is that what is in here is not a north and south pole split apart like we had in this structure here. What you've got here is you've got either a north here and a south here, or a north here and a south there. Okay, but when these two come together, maybe they start spinning like a yin and a yang. Okay, they're spinning around in here. Okay, so you got your iron, and then your carbon, and these are just other elements. The copper. Look where the oxygen is. The oxygen is mostly where the carbon is. Carbon and oxygen. Now look at the magnesium. The magnesium is in these spots. And where are the spots? They're slightly here. They're in between where the iron is. They're in between where the iron is. Okay? And that is kind of true of the silicon. But it's not the same. So look at this. You have this bright area, and we know this has got iron and copper. You have these not bright areas. What is there? We have magnesium spots, but if I put my mouse there, and I click there, you've got a magnesium spot there, a magnesium spot there. You've got a magnesium spot there and a silicon spot. But the silicon is also incident with the iron. See? Iron, iron, iron. Not there, not there. Silicon, 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 silicon. It's everywhere. It's the same story. It's the same story where you have this bizarre, like, waves interfering. You kind of got like, you have a coherent matter wave for iron. You have a coherent matter wave for silicon. You have a coherent matter wave for magnesium, and some of them interact in some of their phases. Or is it just that there's a resonant combination that's singing a song that's able to create that element at that point? Because if you're making coherent matter waves out of one element, then you would expect when it comes out of being in there, it's going to be one element and they'll all be homogeneous. But if you've got multiple elements in there, then you can't imagine that the silicon would be cohering with the iron, and if it's not completely denaturing the elements to the point where they are not elements anymore, they're like proto-matter, or the mother of all matter, as Ken Shoulders called it. You could have like the sphere has different wave packets running around it, and one wave packet is all of the atoms of iron that are going in there acting as one atom of iron. All of the as a quantum unit, whatever you like to think of it as. And then another wave packet in there is the magnesium, and another one is in the silicon. And some of those times they get in phase, and some of them they get out of phase when the whole thing collapses and they come back into our 3 space. So I've done quite a lot of analysis on this, but I just wanted, this actually is an image that was, a section of it was taken to show in the title slide. And what I've done here is what I did before across the bridge, and I did a line sample, and what I did is I tried to go through the center point of each of these circles. Okay, so we've got a circle here, which I showed you before, a circle here, and I drew a line. And here, what I'm looking at is the magnesium is the blue line. The what is it? Silicon is this sort of like pinky reddy line. And then the iron is the green. And so in the first 2 places, as we're tracing across from here, the iron and iron are incident with the silicon. But down here, they're antiphase. The silicon goes up and the iron goes down to flat line. Okay? Then they kind of meet in the middle. Then they kind of stay in phase. And then over here, again, the iron is flatline when the silicon is up. And then up here, you've got the silicon up, and then the iron is up again. Okay, so in this point and this point, they're in phase. In this point and this point, they're antiphase. In this point, they're kind of like 50% between the two. Okay, and then the same kind of thing happens for the magnesium. But in this case, the magnesium is antiphase to the iron. And here it's kind of 50% in phase, 50% in phase, antiphase, 50% in phase. And then when you compare the magnesium and the silicon, outer phase, static, outer phase, in phase, outer phase, in phase, kind of partially antiphase. So, absolutely bizarre. Maybe other people have got a really good explanation other than these are kind of wave packets. And I don't know. I don't know. So let me see if I can, what else do I want to show you? Yeah, there's a lot more data to share, but I think that's probably most of what I wanted to say tonight. So, any questions at that point? Before I go into summary. Any questions? Infidel apostate, you can always do double time on a stream so that you get in phase. Did everyone get my point about the remarkable structure of this weird structure? And these structures are on pits all over this material. So you have a pit, and on one side, and the one that I showed you earlier, well, we'll do it on the review, but excellent, okay. So it just returns back to original elements and no new materials at all. No, well, it depends. As I said earlier on, you can package stuff in an Evo, transport it either in a white mode through free space or in black mode through other materials without anything there. And it can go, without any charge. It basically can teleport through things. And then when you get to the other side, the original material can come out. That's one way. And Shishkin's done, and his team have done a lot of work on that basis. If you push it harder, you might get nuclear reorganization. If you push it very much harder, you then get self-collapse, and you get electronuclear collapse, according to Matsumoto. And then you get electronuclear regeneration, and you get a spread of elements, often carbon, synthesized. So depending on how much you force this, you can do a range of things. You can use it for mining, you can use it for transportation, you can use it for synthesis, you can use it for waste remediation, you can use it for just almost as Ken Shoulder said, if there's something you want to do well, this is probably the thing that does it. Gardy Pierre, what if they've already weaponized it? If I didn't think they'd already weaponized it, I wouldn't have continued doing research in this field in 2017. There needs to be a level playing field. People need to recognize what this technology is and not be fooled. Like we've already got the never-ending terror, the never-ending global climate story, the never-ending virus. We don't want the never-ending threat from outer space from people that might be hurting us, maybe. And please give us more tax money. It's all these never-ending stories which are just getting a little bit tedious. Can you speak to how this rolls out related to Fukushima effort? It's just a real struggle, and it's compounded by the fact that no one can go to Japan at the moment, and Matsumoto is 80, and they've already seen this work, but in 2012, but they didn't know how it worked, so they thought it was an artifact. But now we can show that there is a logical, scientific way that it can occur. There is literature in mainstream literature and in military patents that point to the same direction of the actual physical observations. You can look at this sample every day of the week, and you're going to see the same things that I've showed you today. And with the simple experiments, the Vega experiments, which are relatively simple, but I believe that after Something Electric 2, there will be a possibility for people to explore doing the kind of experiments that are going to lead to positive benefits for possibly as little as $30. So I need to be able to make the case for that. I think with Ultra, there's a good case for showing how that can do this kind of experimentation, but you still need to be able to study the material that's produced to be able to understand it. What I hope to propose with the background is a family of experimental direction that will be cheap, and there is a possibility of immediately and cheaply being able to understand whether it's doing something useful. So essentially what I'm saying in this presentation is there are things in this sample, obviously it being metal and it being probably a cast and an extruded metal, there are things in this sample that are perfectly normal metallic things to expect, both in terms of crystal structure, the formations, the grain structure, the concentration of elements in certain places, and so forth. Then there are things that are not necessarily things you can easily explain away with things that you can go and find on Wikipedia and in the literature. And maybe there are innocent explanations for it. But I believe I have demonstrated today the hypothesis as to why this fractures, why it fractures and these kind of structures fracture in the way that they do. And it is due to the fact of the magnetic structures, the coherent structures that act as one like magnet, and the fact that they can reorient themselves once they're free of their surroundings, and then when the music stops, they kind of fuse back together a little bit and end up with these structures here. And that the actual alloys are important in potentially allowing it to go forward. So if you were trying to replicate Hutchison technology and you thought he just used plain aluminium, a scientist would do this. They would go out and they'd get some very, 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 very pure aluminium, because they would want to see if it produces transmutation. Okay? They would want to see what happens to the crystal grains and so forth. But because John just used scrap and different scrap and put the whole thing into a pile, some things went jellified and some things fractured. Okay? And I believe it's because of the different makeup in the metals why you observed different things happening. And that tells you how you can use this technologically, doesn't it? It tells you what is the important thing to have in a material to be able to do a certain thing. It tells you how you can build EVOs. So for instance, the fact that it looks like it has silicon in here, and silicon and oxygen, as I showed in that ball, means that if this is the thing that comes in between the crystal grains and maybe is on the surface, that might be, in the case of these materials, how the RF that was in the environment that he used was able to convert into vibrations, packets, solitons of vibrations in there that can then lead to coherence. So it might be that different things did different things, but based on the sample element structure. Field interference. Engineering is the closest thing to magic that exists in the world. Field interference, what you're seeing on this page in my book is absolute pure magic. It's just pure magic. This and you know, even if you're saying this is concentrating elements, you know, wouldn't it be great if you could go to a gold mine and you could just take out all the gold and leave everything else in the ground without destroying the environment? That would be just awesome in its own right. If you could get something to go in and just grab all of something of one element. So Axel is saying a triangle is a supersolid form that a very powerful Evo would take on. Yeah, essentially, you see all allotropes of carbon. When I say triangle, it's more tetrahedral, like diamond is one option. Obviously, Bucky, fullerenes, graphite, graphene, carbon nanotubes, those kind of things. Sorry I missed you, Martin. A new Evo may be forming at the center point of the flux tube. Yes, Axel, that might be the case. It might be that the flux tube is coming together, but you see this on solar prominences as well. Something happens at the top and you get these showers coming down, and it might be that there's some mismatch at the top, and well, definitely what you're seeing in this thing that I was sharing with you here earlier is something is coming out of that central section. Let me see here. Something is coming out of this central section here, and I believe it's something to do with where the flux tubes come together. And if you actually look at magnetohydrodynamics, there is an interaction at this center point. And I've shown in other presentations where if you have two of the same pole, they can still interact. And I'm not saying that that's what's going on here, but there's a dead space in the middle. And if there's a dead space, you can imagine things get levitated up and then they just fall down. And that might actually be what's happening. So let me just have a look at this video presentation. So what I'm talking about is, if you look here, we know that these are the same poles, okay, and these are the same poles, and these are the same poles, because they have a hole in the center. If they have a white bit in the center, then they're not the same poles, or this is the opposite pole, okay, and where if this is spinning around this way, in fact, this is a better example. If this is spinning around this way and this one's spinning around this way, or rather, it's moving the material around it rather than it spinning, because I don't think the actual thing is itself spinning, but it's moving the material around it. You can see it's moving the material around, and then it comes off the end here. Okay, in the center space you have it dead, and I think actually in this video I point out that the particle flows like that. And then in here, there's interference. There's interference in this zone here, in this zone here, in this zone here. So what might be happening is you've got like two poles coming together, but they're the same pole, and maybe there's some interference going on. I don't know. I'm not wholly in that, but something along those lines. In the Lion reactor, you saw this very clear. This is the center point, but then the bigger sphere over here comes to the center there, and same here. And I think these are counter-rotating because you have this bit in the center here, and flux came from this side over here and hit the top of this metal bar. And then deposited these this vortical structure on here, which has these crystals that are carbon and so on, calcium. There's no calcium in the material around there, and that's kind of basically what's happening from a north to south perspective in that one. I wonder if the holes were produced by water trapped in it. Maybe that allowed it to start. I don't know. Animating an Evo model is crucial. I wish I could do it. Well, I think I'm going to do that when I have done a lot more work on explaining it. Going through and studying the materials and studying samples and doing experiments teaches you how you should animate it to make it simple for everyone else. Thanks for your kind words, field interference. Okay, so I'm just going to run a quick review of the presentation. Okay, so this was Magic Incarnate, Hutchison Effect, and this is referring to the fracture sample, and we did a deep dive into the sample. There is more data to come, but I think a lot of the important stuff I shared with you this evening. And we discussed the sample, what is probably normal about the sample, what might still be normal about the sample, and why the normal stuff may cause the apparently abnormal stuff, and what may be abnormal at the end. And so this was the sample as received, and I explained that I gave some bits away, and then we had some detailed looks of some macro stack focus shots of it. And then we had a look at the dendritic structures and these cracks and so forth. And we looked at a paper about dendritic grains. Then we looked at different quanta of evos on there. And I showed something which I wanted to show in the previous presentation, but didn't because I didn't have it easily available, where this particular evo quanta is from a different angle, and you can see how it's cut out, and you get this kind of like shape formed in the center. And this head you're seeing here is the head that you're seeing in the center here, slightly off to one side. And we've got outies and innies, are two charge types of evo in this form. And like I say, these can cluster together, and they can go in pairs, and even they can come together as north and north and south, and they can, if you had many norths, you could imagine that would become a north pole monopole, even though they are themselves. But they do appear to be able to cluster and quantize up by joining together. And the largest one that I've observed on this particular Hutchison sample is 1.6 millimeters across, and always with a D4D ratio, and they're pinched on the inside, and we discussed that in the past. And then I said that they can cluster and then form a skin on material, and I discussed that maybe these are synthesized by the evos, or they are organized by the evos, or they are left over from some sort of casting technique. But you can even see like sticking out the top here. And the fact that on the quartz from Lion, you saw the same thing going across the edge, but still leaving the edge intact. So it's like a surface effect, but it was clear to see that it was a surface effect in the Lion dual sample because it's a clear amorphous substance, whereas we know that the aluminium will have other phases of material in it. But they're at the same scale, and we've got outies and innies in this as well. And then I talked about how Ken Shoulders made a few points in his interview with John Hutchison in 2010, which you go and look at on our Steemit channel, and how anti-gravity and propulsion and energy source are all possible, as well as teleportation. But the key point that I was drawing here is that it can enshroud stuff, as we were discussing here, by merging together into one sort of homogeneous kind of thing. Although it's not homogeneous, I have to say, it's kind of like lots of units, but they kind of link together. It's like a getting some chainmail and wrapping it around something, and then it kind of shields the stuff inside. And so I showed some close-up of the Lion, and I discussed how this is effectively like a Star Trek shield, although there is still some effective change on the quartz. It does convert to rose quartz, which does mean that beta particles and X-rays are going through, because that is how you make fake rose quartz, by treating it with something like cobalt-60 and heating it in an oven. Well, the oven's already there in the Lion reactor. And otherwise it would have looked like this smoky green quartz affected material here. And then I did a deep dive into this to argue the point that these intersecting evos, which are 50% into the material, are meshing together. So you have one that is intersecting this one, and that one's intersecting that one, just as I showed you with the hydrodynamic systems. Here's our individual ones. There's two meshing together in our classic heart shape, and this is an individual one on its own. And then I talked how the 1950s work can lead very easily with the Ken Shoulders patents to making this room temperature superconductor, and that this effectively is a skin, a envelope of coherent matter, and that leads to he's saying that EVOs don't obey fluid laws either. God, I'm tired now. And it's a superconductor, and essentially then if something's enveloped, you can make your magic carpet, as Ken Shoulders likes to call it. And so this, I believe, is an example of superfluidity, and this would be the iron that's either captured from the aluminium or synthesized from the elements that are in there, the magnesium, the silicon, and the aluminium coming together to make iron, and that this is a very, very thin layer that's coming over here. And then I showed that this cannot possibly be due to pinching effect, which I originally thought it was on these ridges, because it actually is traveling up and down and up and down and up and down in a 90-degree line across here. And if it was caused by the pinching, then you would have a pinch that goes this way, but you just don't. So it's more complicated than that, and I believe that this material is really rather amazing. And so I then talked about magnetic monopoles and the fact that I'd come to the conclusion by sort of I don't know, in 2019 or something, that this had to be the way, and I started rolling that out last year. And then I was talking to John about it, and he said, "Oh yeah, that's what George Hasseray thought it might be." So I then basically concluded that when you combine that knowledge with the way that iron may concentrate in grain boundaries, then you might have a scenario where the iron plays the same role as it does here, but only in the grain boundaries, and causes the fracturing and skinning of the crystals and the long crystals in extruded materials to cause the splintering of the samples, and then rearrangement based on their magnetic poles, and then fusing when the music ends. I talked about a particular effect in metallurgy which may explain these lines but not Lauda lines, and then I gave an explanation overview slide here of how that occurs, and then I started talking about previous presentations here that we've talked about in the past about material organization. I then came on to this one where I was talking about the bizarre arrangement of where you have some elements in one side and not other elements in the other side, but they have different combinations. But so basically silicon on this shape here, and calcium, and then the other side has iron and silicon. So it's just a bit bizarre. And then you have one that has iron, and this has no oxygen with the iron, but this has oxygen with the iron, so it's just weird. Could it be magnetism? I think it's probably something to do with that, and its affinity for electrons and so forth. And this is another slide, and this is a whole other subject. And then I got on to the bridge and the hole, and we talked about how this is a flux pipe, and that this might be basically a yin-yang. And this is maybe a whole sphere. It might actually be a sphere of EVOs, and that is spinning maybe or something, but it's eating into the material, it would appear. And these are not unique. There are a good number of these over the surface, and they tend to have these on half a side. They have something that they seem to be chucking out, and then there's a bleed at the center point that puts this superfluid material across the surface. And at the center point of this bridge, which may be a north-south pole flux tube, at the center point, copper and iron and silicon and even tin are synthesizing, come out, and then you end up here with something that's silicon and calcium and oxygen, and over here you have iron and silicon, and that this looks like a structure that was laying a slug trail of this iron superfluid material behind it. And then we have another flux tube over here, and you can see the helical structure of it very much clearer than on this one. And so I looked at line samples and spot samples and so forth, and I went into great detail on the hole, and I talked a little bit about this, and that's about it really. And I introduced that again to argue that that might be something to do with what we are seeing in the hole. I think that's about it. So any questions before I call it a night? Like I say, next week I hope to do something electric part 2. So this time next Sunday, roughly. And I think it's going to be really, really rather special. But I think what you can see from what I've shared tonight is that if you only look at John Hutchison samples at a cursory level, you will only see things you expect to see. You have to spend a lot of time studying it, thinking about it, and so forth. And even though that has been the case, I've put out a couple of challenges where the first challenge you could win, or not win, you get sent one of these if you come up with an adequate explanation. And then the second one, I can't even remember what it was for, but at least one of them was for, you can go and look at the video, was for this iron that's able to go across the surface and crystallize. I'd like to see that. Well, the copper might be made magnetic because EVOs like to live in copper because it's a metal and it's highly conductive, and the EVO clusters themselves can become suppressed magnetic monopoles. So they're pseudo-magnetic monopoles. They do have another pole, but it's not very strong. Hey Bob, how does anti-gravity come into play? I need to do a whole series of things to explain some underlying concepts, but go and look at the promotional video for the Kickstarter for this book, and on our YouTube channel. And in there, I give, I think, 5 scientific papers with a QR code. You can look at the QR code and go to the scientific papers. And I think if you read through those, you'll have a reasonable idea of the relationship. And then if you look at the... I actually, that guy, John Wheeler, who I talked about in last week's presentation, I didn't realize that the guy actually invented the term black hole and a wormhole, and he was instrumental in the N bomb and the H bomb, and I think he was the guy that kind of basically designed, or was in principle designing, Ivy Mike, which produced a 30% bigger yield in Enewetak Atoll. So the guy that I was discussing last week, having only heard about him the day before, who came up with Gions, he's the guy that's partly responsible for making the mess that I want to clean up in the Enewetak Atoll. But anyway, the point being is that the EVOs itself are bound together gravitationally, according to him, because his structure looks pretty much like the structure that I derived from physical evidence from John Hutchison's materials, and specifically from this one. And Matsumoto and other authors claim that when you get the cluster and it's wetted and it's in this state where it can do its self-compression, that is a gravity collapse. And so you can imagine that if you have the gravity vector that holds the EVO together, all pointing in the same direction, then they might get to a point of doing a self-collapse. Now, if you were to skin, say, a cannonball with these things, the thing that's causing gravity may not see it. The action of gravity may not see it. And that might explain some of the observations that we see in the Vega experiments. Yeah, so it looked like a different metal. I imagine that it would have been converted to iron. You can do the reaction tables. Maybe I can do that for you right now. Let's bring up. Let's go here. We go to Nanosoft. Philip Howe's wonderful database, the MFMP's reaction database calculator. So if we wanted to say do a 2-to-2 reaction, and I'm going to put in, let's make that a little bit bigger so it's easier for you to see. I'm going to put in Cu and Cu here, and I'm going to see he'll hate me for doing this, getting rid of that. Just see if I can see in the first 1,000 answers, do I get any Fe? Do I get any Fe? There we go. There we go. So if you start with copper and copper and you put them into an EVO and you don't drive it too hard, and you are going to get nickel and iron. You can get iron and germanium and iron and germanium. So there's a path there to getting iron, and there's a net yield there. Okay. So both nickel and iron are obviously magnetic. And the most likely product there is there's a reasonably even ratio. I think it's 65-35 or something like 55-45 or something. I can't remember offhand. For copper and isotopes, there's only 2 copper isotopes, so 63 and 65. And so the biggest energy yield, which is the most likely if you have the most pressure on it, is producing nickel 62, which is a very rare isotope, or not the rarest, but very rare, of nickel. And that is magnetic. So every single reaction that you see producing there is producing a magnetic particle. So yeah, I think I used that in mining diamonds with Lion, where someone had the copper sample and it had the inclusions in there, and they were using one of these magnetic things, one of these like this, and you get a magnet and it shows the poles. Honest, like so. There we go. Magnaview paper. And they were putting that over, and they were seeing not only was there a different coloured material in there, that where that coloured material was, it was producing magnetic signature, so it was actually magnetised. And so I imagine that if you look at the reactions that I'm showing you here, if you start with copper and copper and you squish it, the available options for it to squish to are nickel and iron. Hi Simon, great to see you. Yeah, so the thing is, after a while, like with the reaction calculator and you know, if you push it too hard, you will get transuranics, and they will fission, and you'll get radiation. And this is what Leclerc saw, and this is what Adamenko saw. If you have lots of light elements in there and heavy elements together, it'll try and find somewhere in the middle, depending on how much intensity you do it. But if you've just got pure copper and pure copper, you're seeing that it makes nickel and iron, and both are ferromagnetic. So it's not surprising that that's what's happened. The logic is consistent throughout. And this is why I'm saying, when I found out that the cooling of alloys produced ion concentrations at the grain boundaries, it became totally logical to me that the reason this happened the way it did was because it was doing the same thing, but in a slightly different way as the splitting of the iron rich rat tail file, where the material nucleates, it grows, and the thing is, with pure aluminium, the EVOs can move around because they're not locked to something that's magnetic, so they can move around, and that's, in my view, why it jiggles. It jiggles. If you've got waves that are not perfectly standing, then they will move around, like you see in the ultra experiments. That's why I love the ultra experiments, because they're such a wonderful analog for magnetohydrodynamics, because they're hydrodynamics. You are able to start to understand what's going on with manipulating the ether, but by watching a different fluid, where it's not a superfluid, so you don't have to work in. Superfluids will move very, very quickly. There's no resistance, so having a fluid to work with, you can study the process at a speed that you can just about attain, because it's still very quick. You need fast cameras with high resolution to understand it, and we're getting there. I mean, it's just, I have to say that Martin Yamas has done some even better work this week, and so, you know, I think we'll be able to learn a lot from ultra, regardless of the fact that it's transmuting anyway. Even with 100 hertz vibration in a Masa tanks, which means it basically every time there's cavitation anywhere, there's going to be transmutation. But from studying the fluid dynamics and then projecting that to magnetofluid hydrodynamics, it's a useful thing. Field interference. Do you know anyone currently trying to replicate the Hutchison effect? There's probably lots of people trying. I suspect that the very part of the reason he was very successful is that he was using scrap metal, and he was putting a pile of metal, and some of it responded. And the reason is some of it had the right crystal structure and the right place at the right time and the right thing. Whereas I think many people will have probably failed because it was the same with Pons and Fleischmann. It's only almost in the last 5-10 years that people have realized that it was the impurities in the original Johnson-Matthey electrodes that were the cause of the thing doing the thing in the first place. The impurities. And so a lot of people went out and tried to replicate it by getting the purest palladium they possibly could. Epic fail. And I think probably many people that would have attempted and been capable to have done the Hutchison effect failed because they probably tried to do it too scientifically. And sometimes you just don't get things done by trying to do things too scientifically. Sometimes you do, but sometimes you don't. And in this case, that's one of those times. But I think it happened. It showed what was possible. This is real. And certain aspects of the things that we observe in these samples, we have seen in other technologies. So the active agent, as I called it, and the Russians like to call it, that is real, and it can do amazing things. That's interesting, Alan. The Philadelphia experiment that shrunk the ship. I think more worryingly is that the parts of the ship apparently became able to be intersected with biological matter, and that's as I understand it. But I don't know. It's half fiction and half truth. That's very interesting. I would be interested to find out, WP for Truth, what the black tiny balls were. Did you collect some? Field interference. You need to make the EVOs. The EVOs can be made in situ if you have the right things in play, or you can make them and project them onto something, and then if it's a good receiver for them, like a metal, a conductive metal, then they can accept them, and then you may be able to energize them once they're in the material. I'm working back from physical samples to what must have happened, and you know, there will be dead ends along the road, but the samples can't lie. They can tell you things that are already known to science, and trying to separate out what is interesting from what is mundane. And it might be actually that what is normally considered mundane and well known, there's actually more to it. There's more going on in the story of how certain things happen. You know, yes, we can model it. We can use these equations, and it does this. This is how we can see our dendritic crystals grow. But there might actually be something going on at a different level that isn't so obvious, other than being able to just, you know, you might have the wrong equation that gives you the right answer, but it doesn't work in every situation. But it's a good working framework. So it may actually be that when you look at what I'm sharing and you look at the scale, that by looking at the ridges and the different frequencies on those ridges and the interfering fields, that you can work out, given the speed of sound in the metal and given the speed of other waves in the metal, that these frequencies must have been used for it to have taken place. But ideally, you would want to know the length of the sample and the width and all the parameters of the sample, and then have the SEMs to study to see how things played out in the flesh when you look at it, and then kind of like work back from there. I mean, if you look at this slide, for instance, you're seeing these bands. Are these bands relevant? Is this big band here and this trough here and this band here, are these relevant across this field here? When you're looking at this, are the distance between these spots relevant? are the distance between these bands relevant? Are the distance between these little striations here, are they relevant to what the process was that caused it to happen? Time machine. I need a time machine now. It's 1:31 here. I think I probably need to call it a night. I think you can use this to pause time locally for the thing inside. I think once you're inside the coherent matter structure, time doesn't really affect you. But the problem is that then also you will have a problem with consciousness. So, you know, you won't even know you're not experiencing time. So you could make a structure, go into it, time will go on as normal outside, but you inside, you won't age, and you won't even be aware of the passage of time. And then if for whatever reason the structure fails around you, you'll come out not knowing how much time you spent inside, but you'll have effectively traveled forward into the future. You won't have aged, and you will be in every way the same, but you'll just be in the future. Not sure how you can go back in time. I'm not sure how you can go back in time. Okay, so I'm going to say thank you very much for your time. It's been a real pleasure to finally get this data out, at least in a fairly rough form. I will, maybe not next week because I'll be preparing for Something Electric Part 2, but I will revisit this material, and I will share the slides, and I will also package up correctly labeling with Alan Goldwater's logos, because really this work would not have been possible without his sacrifice to get that scanning electron microscope. And I think, like I say, there's even more data to share, and so it's a lot of work. But I think really we're getting to the bottom of how I think we already knew to a degree. And it would appear that it was understood a long time ago by George Hathaway that there was probably some form of magnetic monopoles being formed. But I think we're closer to understanding why different materials exhibited different effects. And it's really down to their elements and the structure within them. So thank you very much, Simon. Thank you, Field Interference. Thank you, Artman1. Thank you, WP for Truth. Looking forward to your videos, and really enjoy your week. And it's getting nice and warm here. And I don't know if you noticed, but I managed to hand over my papers and was permitted to have my hair cut. So thank you very, very much. And I'll say good night, sayonara, dobro noc, buonasera, bonne nuit, and I'll see you next week.